And welcome back, ladies and gentlemen, boys and girls, angels and demons and monsters and serpents, to Brothers of the Serpent podcast, coming to you not live from the 10 by 10 by 10 tangent cube of science, nestled amongst the dusty bones of an ancient seabed, high atop the Edwards Plateau. So we're using our emergency backup podcasting day Thursday because
That's right.
because on Wednesday, the day that we normally record these days, well, okay, it's kind of a long story. The day before that, Tuesday, this is how it actually happened. On Tuesday, I was feeding the bees. So out at the orchard / vineyard, we do have some beehives. I don't know how much we've talked about that, but I try to follow the philosophy of leave the bees alone as much as possible. That's what I've been told by the good beekeepers that I know. They're like, these bees know more about beekeeping than you ever will, so leave them alone as much as you can. But it is fall going into winter here, and it is winter.
And we've placed their hives in a place that they didn't pick, so...
Yeah, so feeding them is a good idea. And so I was going to check on the food levels, and it was a windy day, right? And so normally I would use a smoker, and kind of that calms them down. But it was windy and I couldn't find the smoker anyway. So I had to go check the food levels because the boss wanted that to happen. So I opened up the hives and I'm working on it. And I have this, the bee suit that I have, it's a full body suit and it's called the French style, which means that the face shield is basically think of a hoodie hood with a mesh over the front of the hood, which would normally be the open part if it was just a hoodie. It's a little thicker than a regular hoodie. It's kind of, strong. It's got mesh all over to protect you. But the way the face shield works is basically you're wearing this hood and the back of your head is against the hood, the back of the hood. And that puts the mesh maybe 6 inches in front of your nose so that bees can crawl around on the mesh and they're not actually on your face. Well, at one point when the bees were really mad because I had just cracked their hive open to check the feeder, I turned and this big gust of wind pushed the hood back and pushed the mesh against my face. And I had all these bees all over the mesh and probably two of them, maybe, I don't know if it was two. I thought it was one at first, but I got stung basically on the forehead up by the hairline. And so, yeah, I learned a couple things. Don't mess with the bees on a windy day, especially not with that particular kind of bee suit. But anyway, later that day, my eye started swelling up on that side of my face. Like I had gotten hit, like I was in a fight.
Yeah, you look like you got nailed in a fight.
But it was weird because the spot where I got stung way up on my forehead was not swelling up. It didn't hurt. The initial sting obviously stings or whatever. But like 4 or 5 hours later, basically, all around my eye starts to get swollen. And I went to bed that night. And when I woke up the next morning, I couldn't even see out of that eye. It was completely swollen shut. I could not open it even if I tried. So I was basically effectively blinded on half of my face, and that whole area was all swollen, and it was annoying and itchy. And so anyway, I postponed the podcast because
couldn't read,
can't read anything, can't see, can't drive,
couldn't play video games.
That's right. It was a pretty boring day. So it's still a little swollen, but it's open now, and I can see through it. So.
Here we are.
Yeah, I'm here with a swollen face, but at least I can see. And we are actually joined today again by our good friend GMA. He is somewhere in the four-wall project that is his house.
What's up, snakes?
Hey, GMA. Yeah, so he's joining us remotely. Yeah. And he's going to be here for the whole show, so he's going to be chiming in whenever he wants. But mainly we've got him here because we want to do some follow-up on the Tesla episode. Right, GMA?
Oh, yeah.
Yeah. So one of these segments, probably the second segment, we'll start in on that and go through some of the follow-up stuff we wanted to do, dealing with people's questions and other discussions that the three of us had after doing that show. So looking forward to that. But for now, let's go ahead and do Space Weather News from spaceweather.com. Uh-oh. And I don't have it up. Here it is. Crescent Moon joins this great conjunction. So when the sun goes down tonight, which is too late for that, guys, step outside and look southwest. An exquisitely slender crescent moon is approaching Jupiter and Saturn on the eve of their great conjunction. They form a must-see trio on December 16th and 17th. So sorry to everyone, this is too late for you to use.
But it was beautiful.
Yeah.
Last night especially.
Right.
With the crescent moon, and then of course I think it's the light from Earth that's shining back on the dark face of the moon that kind of brightens it just a little bit.
Yeah.
And so you can see the whole thing, but the crescent is bright.
Yeah, the Earth shine is lighting up the dark side of the moon. Yeah.
It was awesome.
Yeah,
The two planets were
it's
there.
awesome looking for sure.
Yeah. Yeah, and they have a picture here showing the relative positions. They're getting pretty close.
Yeah.
So they say this must-see trio is followed then by the Great Conjunction itself on December 21st, and no telescope is required.
I'd say right now they look like they're about a half a degree of arc apart.
Yeah.
In the sky.
Yeah. Yeah, and it's
Jupiter
pretty
and
awesome. I keep seeing people saying, "Oh, well, this happens every 20 years," and that's true. The Jupiter-Saturn conjunction happens every 20 years. But the last time they were actually this close, and I think we went over this maybe last show or the show before. The last time they were this close was in like the 1200s, like 1220 or something AD. But the last time that they had this kind of conjunction on a solstice, I haven't even been able to figure out when that was. I'm sure somebody could calculate it, but that's what
Would it be right?
Yeah, I don't. Yeah, there you go. That's a good
after
question.
all everything that we've learned, I don't know
maybe
if it'll
not.
be right.
It may not be right.
Have to look at the annals of Chinese history.
That's right. All right, current conditions. Solar wind speed is 260.5 kilometers per second. The density is low, 2.5 protons per cubic centimeter. Current sunspot count is 12. So obviously we are a 0 spotless day stretch. And 2020 total spotless days is 59%. So it's been dropping a lot. I think we were all the way up at 77 at one point earlier in the year. So yeah, as solar cycle 25 ramps up, spotless days go down. And let's see, the neutron count is rated at high at 8.6% above the space age average. And the KP index is 1 quiet right now. But I guess we had that flare in the CME hit us earlier, and that made the KP go up, and then it went back down pretty fast. Yeah. But right now it's all quiet on the KP front.
Yep. So what did you think about that, GMA? We were talking about the KP index and the oscillations of the Earth's magnetic field, especially back in ancient Earth history when the magnetic field would have been much more powerful. How that could have affected the way technologies were advanced in terms of electricity, because if you have really good conductors and there's a fluctuating magnetic Earth field and a very strong magnetic Earth field, maybe you just have, you make stuff out of gold and it just has electrical properties.
Oh, yeah.
Right? It's in
Yeah, I was listening to that when y'all were talking with Laird, right?
Yes.
Yeah, that's an interesting thing to think about. I don't know what to think at this point, except like you said, stuff like gold that is already a great conductor could exhibit properties that we don't even think about today.
Yeah. Yeah, I think that's. I mean, is there a way to research it? That's the question. Could we artificially simulate this environment? That seems possible.
Yeah, make yourself a big enough coil, get yourself a big old magnetic field going. You know anyone with one of them magnetic wrecking cranes?
Yeah, that would be. I'd love to have one of those. All right. Well, I have lots of stories, and I have a bunch of emails. So we should get into the emails first. What do you say? What do you think?
Sure.
All right.
Yeah. You want to do that?
Yeah. Let's do some emails. Let me make sure I'm in the right place here. Okay. So we have a bunch from Roddy. So I might group all those at the end because he actually sent us a whole bunch, like 4.
Oh, wow.
Yeah, he's been listening to the Velikovsky heresies and his brain's going.
Okay, cool.
His furry mind is working hard. Okay, so this one's from Sarah. And it's called Snake Farm. It's a reptile house. It says, "Hi, Snake Bros. I did a podcast search a few weeks ago looking for something about Glacial Lake Agassiz. And it brought me to Cosmographia. And that subsequently led me to Use Guys. I love your podcast. The only annoying thing, which is not your uproarious laughter, that's great, is that I heard a song on public radio several times in 2010, and I always think of it when I hear the Snake Bros. It's called Snake Farm by Ray Hubbard.
I've heard that.
Have you heard it? Apparently, it is imprinted deeply in my brain. Sigh.
Yep.
Another annoying thing, I unwittingly managed to get my husband hooked on the podcast as well, and now he won't let me listen to any episodes unless we're together. Pain in the ass. And why aren't there more she snakes in your episodes? Snakes! Well, we did have Laura, the snake sister, snake wife, in on the
Gods of
Eden episodes. So what was that, 7 or 8 in a row, something like that?
Yeah.
Yeah.
Yeah, I think our first guest was Patty Canup from Rockwell?
Our first guest was Thomas Spriggs.
Oh, okay. Second
The
guest.
second guest was Patty, yeah.
Yeah.
That's right.
What are you talking about? We're not a guest-heavy show.
That's right.
We don't discriminate. It's just about, who brings the materials.
That's right.
all.
Okay, so this one is interesting. This actually originally was sent to the Cosmographia show. I am connected to that email, the cosmographia1618@gmail.com. So people email that address when they're talking to the Cosmographia crew. So I have access to it, and so I do go through a bunch of them. And this one came in, and I was just like, man, I want to read this on Brothers of the Serpent. So I forwarded it to myself from the Cosmographia email to the Brothers of the Serpent email.
So now it's legit.
That's it. Yeah, it's totally legit. This is sent to us. This is from Bryce, and it's called Anecdotal Evidence. It says, "Gentlemen, around 1960, I was a Boy Scout in Wichita, Kansas, on a field trip to the Friends University Museum there. This was a rather small collection of Kansas history items. On this occasion, our group was being guided by an older gentleman who showed us a small stone figure of a human about 2.5 inches tall. It was made of a white-colored stone with one leg broken off. There was little detail, but clearly it was human. The guide said it was donated by a guy who said he found it in a drill core at an oil well from 1,500 feet down. He noted that would be unlikely because it was too deep to find artifacts, but your work regarding massive meltwater floods has led me to think it really was indeed possible. Thanks." From Bryce.
Yeah, that's really cool.
That reminds me of the Nampa figurine, which was found from 300 feet down while drilling a water well.
I wonder how this takes place. Like, how does a figurine that fragile and that large...
Well, in the case of the Nampa figurine, it came up with a sand pump.
Oh.
Because, once they penetrated they penetrated the volcanic rock down there, they stopped using the auger, and they started using a sand pump because it was just like sandy slurry. So it just pushes water in and then pumps it out, and the figurine came up in that stuff. I don't know in this case.
Because I'm looking at this this drill head.
That, you're like,
Eldor sent us, right?
Yeah, Matt. Yep.
And I don't know how that could preserve a figurine. So it must not have been something like that.
Yeah. Okay, this one is...
But wait.
Okay.
Going back to the first email real quick, I want to say, welcome to the show.
Oh, yeah.
Thanks for joining.
Yeah.
We really appreciate you. I just got stuck on the last comment. Totally sidetracked by that.
Oh, yeah. Why aren't there more she snakes? Okay, this one is called Mass Extinctions. And it is from Let me make sure I do this right. Istvan. Yes. It says, "Hi, Snakes. First of all, thank you very much for all the hard work and for giving us an amazing podcast for free. And of course, Cosmo with Randall Carlson." He says, "I am happy to announce that I am all up to date with your podcast, so now I am part of the sad group of listeners waiting for a whole week. One podcast a week. What a joke. LOL."
No. This is the answer to the, will you do more podcasts a week? No.
Russ, I have to tell you something. My favorite is Kyle. And he said, "I expect Snake Bro laughing here." So yeah, you got it. "Merry Christmas, guys, and a very happy new year. Istvan from Salzburg. P.S. The S in my name is pronounced as S in rush, and the A is like A in car. A quick Hungarian lesson, but I don't mind you butchering my name. Ha 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 ha. So I try not to butcher it. Istvan, I think, is how that's supposed to be said. So let me know how I did. But thanks, buddy.
Good pronunciation notes there.
Glad you're enjoying the show. Oh, and he also sent us a link to an article which I'm going to be reading later about mass extinctions.
Oh, okay.
So that's
cool.
why the email was titled Mass Extinctions. So yeah, thanks for that link, buddy. I'm definitely going to read that on the show. Okay, we got. Let's go ahead and start with Roddy here. Yeah. First one. "Dear Ophidian siblings, sitting here before the fire, cup of tea and purring feline by my side, and listening to the 4th installment of Velikovsky, and had yet another thought. Why is the Earth's crust fractured? From what I can find, both Mars and Venus appear to have intact crusts. Even the moon, which is thought by some to have been created from a collision with a young Earth, seems to have a solid, intact crust. So why does the Earth look like a fractured egg? Could it be that it was hit, perhaps several times in the past, by large, maybe planet-sized celestial objects? I know geologists have traced the paths of the continents all the way back to Pangaea, but has any scientist examined the pattern of tectonic cracks to see if there is evidence of a rather large impact with another object? Your ever curious and warm-blooded friend, Roddy the Mammal." So, I tried to look into this, and it is interesting questions. First of all, there is... Okay, so the subject of Mars's tectonic plates is in dispute right now. There's people that think that it doesn't have any, but there are other people that think that they are finding evidence of faults. But it's, this is all, for the most part, this would be satellite imagery data on Mars. So they're having to look down, like, Google Earth for Mars, basically, from the orbiters we have. But there's some pretty good evidence and some papers that have been written that are saying what is it called? The Valles Marineris, that giant canyon, is actually a transform fault, like the kind that Johnson was telling us about, where it slides sideways. It's the same kind of fault that made the Dead Sea. And that's the reason why the Valles Marineris is this incredibly deep canyon, not because it was, formed by water, but because it's an actual transform fault. So there's arguments, and also they've found evidence in some cases of magnetic anomalies in the crust that look the same as what Earth has in some cases around faults. And also the same kind where it's the field seems to be one way in a band and then another way in another band and another way in another band, implying like how Earth makes crust on the ocean floors. So there's also an argument on whether or not Mars is active presently in terms of tectonics, or whether all of this, if this is evidence of tectonic movement, whether it's incredibly ancient and it's now totally stopped, or whether it's actually pretty young and is just getting started. So that's pretty cool. As for Venus, yeah, Venus is harder. It's impossible to see the surface from an orbiter, except for using like radar and other things like that. So whether Venus it seems to have a single crust, but it's not clear.
But aren't there geomagnetic fluctuations during earthquakes on Earth?
Yeah.
So is it possible to detect those from an orbiter?
Yes. Yeah.
So they could
So
see.
one of the things I was reading about Mars and its possible tectonic activity is that they're thinking maybe there are Mars quakes every million years or so.
Oh,
like
wow.
it's incredibly rare, and that also
Probably means it's every 23.4 years or something like that.
right. That also is, and it's the same whether it's brand new and just getting started or incredibly ancient and slowing down and stopping.
Yeah.
Right. Now going back to Earth and its tectonic plates and why they're there. Like there's all kinds of ideas, but nobody really knows. But as far as I can tell, the prevailing idea seems to be having something to do either with overheating or an overcooling of the Earth's crust deep in its past, like 4 billion years ago. Either one of those, whether it cooled very quickly or it heated up very quickly, would crack it. And it's been cracked ever since. And then, of course, the moon going around it is dragging it around all the time.
Mm-hmm. Large moon.
Yeah. But could these tectonic faults be from impacts? I mean, yeah. I didn't see anyone talking about that, but that doesn't mean it isn't true. They're not really sure. And obviously, if the idea of the creation of the moon it resulted from some enormous impact deep in the Earth's past, that could be the cause of the fracturing.
Yeah.
So, but yeah, I don't know if you can use the pattern of the tectonic plates and where, what the pattern of them is to try to roll everything backwards and see if they resulted from impacts. That would probably be almost impossible to model. And then it would only be a model, even if you could do it. Right?
Yeah.
But I think those are good questions. All right, next one. This one is slightly less politically correct, but it's okay. Venus, the hysterical planet, from Roddy. Dear Ophidian siblings, just reading about Venus and the Velikovsky heresies by Laird Scranton and was smacked upside my furry little head with a thought and observation. All the planets in our solar system are named after male gods, at least in the Greco-Roman world, except for the planet Venus. Is it possible that pre-1500 BCE, when mapping the celestial world above, the ancient astronomers noted that all of the celestial planets observed only Venus had an irregular and disruptive orbit, which, to these ancient minds, suggested the more feminine, hysterical aspect of the nature world. Could such a male-female naming of the planets be but another small puzzle piece to fit into the larger puzzle of the possible origins of Venus? Further, it would be interesting to learn if such a pattern of masculine and feminine planet naming was repeated in the astronomy of other ancient civilizations. Endothermically yours, Roddy the Mammal.
That's a really good point, though.
P.S. Congrats to Kyle and Laura on the forthcoming snake cub.
Well, thank you, sir. Yeah, we're looking forward to it. But that's a great observation.
Yeah.
Never thought of that. And, I totally think that I mean, you got all these, the men are the ones naming the stuff, right? Back in those times. So, yeah, they would be picking things based on their perspective.
Right. Yep.
So that's interesting. But I was...
Now, plenty of the moons, the planetary moons, have female goddess names, but, those weren't usually named by ancient astronomers. So... but yeah, it is an interesting idea. I guess the question to dive even deeper into the question is, you would want to look at whether it's planets or not. So you would want to look at ancient world mythologies and, like Laird says, and find the god that is born into the myth, into the pantheon, and then find out if that was always a female.
Mm-hmm. Good point. Yeah, but there are other masculine, feminine aspects that we get from our ancestors, like the circle and the square.
Yep.
The square is masculine, the circle is feminine. And this also, you could see, like, the naming convention is coming from dudes, because they're like, squares are simple and you can totally understand them and they make sense. Circles are impossible to figure out. And it's the same with the sun and the moon, right? The sun is the daytime when you can see everything and everything's understandable and navigable. And the moon is the nighttime when you can't see, and you don't know what's going on. And
Yep.
so
Yep. I've been going through the secret teachings. I'm reading the plates for the audiobook that I'm working on with Graham and Darren from Grimerica, and he just was going through the whole gold and silver and alchemical meanings, and how gold is masculine and silver is feminine.
Yeah, I mean,
gold is associated with the sun, silver associated with the moon. Yeah,
Yep.
yeah.
But the square and the circle are that's great. Okay, the watcher is saying hurricanes were all named after women originally because they were erratic and unpredictable and seemed emotional
and destructive.
Okay.
Wow.
Jeez. So mean, dudes.
Okay. Part 3 from Roddy the Mammal. Addendum, Venus the hysterical planet. Dear Ophidian siblings, another thing regarding the origin of Venus. Since learning of Velikovsky's theory, I've oft wondered if the great eye of Jupiter is but a remnant or signature of some celestial collision with an Earth/Venus-sized object. Imagine the size of the scarring crater that a collision would leave, and the effects such a crater might have on the swirling, windswept weather patterns of Jupiter. As always, Roddy the Mammal.
Which one was it? The eye?
Yeah.
Okay.
The Great Storm. Yeah. So the weird thing though about Jupiter or any gas giant is there even a surface for it to leave a scar on?
I can't imagine there's not. I don't know why, but it seems like when you get down far enough, everything's under so much pressure that it will be solid.
Yeah. And because matter acts it has like phase changes.
Yeah,
there might be definite discontinuities.
Yes. Yeah.
But
the other thing
it's going to encounter liquid before it encounters solid if it is all gases, right?
And also, these things, their thresholds change with heat and pressure.
Yeah.
Which are very, interchangeable or very closely related to each other. So the deeper you get, the higher the pressure, the more heat.
Yeah.
And so you can maintain a gas under extreme pressure and heat for longer than it would. Right.
Yeah. But at some point, it's going to be a liquid.
Yeah. At some point, it'll become a liquid
and it's also, there's probably been precipitation of some kind.
Yeah.
Right.
But if there's all kinds of crazy lightning storms like down in there,
who knows what's happening?
Changing stuff. And I don't know. Who knows? Yeah. But I don't know if any of you have watched the new Lost in Space series, but Laura and I just finished watching the first 2 seasons. Crap. All right. I just realized it's a spoiler alert, but I mean...
Spoilers.
Anyway, there's a really great scene in there of a gas giant and them like cruising down into the atmosphere of a gas giant. So I'll just say that.
Okay.
And we've actually discussed these possibilities before on this show, and when I saw that scene, I was like, ha ha!
Ha ha!
They've been listening to the podcast.
All right.
Anyway.
All right, final email and last one, part 4 from Roddy. He says, Velikovsky, a further observation. Dear Ophidian siblings, about a third of the way through Velikovsky heresies and came to an observation. Statistically speaking, given the expertise of the scientists of the 1950s and lack of expertise of Velikovsky, the scientific predictions of said experts regarding the nature of Venus, Jupiter, the magnetosphere, etc. should be far more accurate than Velikovsky's predictions. However, the reverse is true. Velikovsky's predictions have been shown to be far more accurate than the predictions of the experts, far more accurate than coincidence would or could explain. So I love this book. Thank you for introducing it to us. Endothermic regards, Roddy the Mammal.
Endothermic. That's this new sign.
Yeah, mammals generate their own heat.
Yeah.
We get it. And yeah, we talked about
well, with
this.
the warmest exothermic love. We appreciate your emails, buddy.
And we talked a lot about this. There's ways to measure this accuracy. Velikovsky it did seem that he made quite a lot of predictions, and they seemed to be outlandish at the time, and a lot of them panned out or have yet to be shown to be false. So it's very interesting.
Yeah.
Some of them didn't pan out, but in a lot of cases they did. So I I think that what I recall the best on this is that letter that Velikovsky received from Harry Hammond Hesch, his friend, who basically said, that you made lots of predictions. Some of them came to be true, even when at the time of you making the predictions, no one thought they could be possible. I'm not aware of you ever making a prediction that didn't come true. I still don't really believe everything you say, but I believe you deserve a fair hearing. And then at the end, he said, I think that the reason you're able to do this is because you have a good grasp of the natural sciences, and perhaps you are not bound by the conventions and probability calculations that the rest of us are.
Yeah.
So, Yep. All right. Great emails from everybody. Thank you guys so much.
Yep.
And remember, you can always email us, brothersoftheserpent@gmail.com. If I don't read it on the show, just keep sending them. I read them all, even if I can't read them all on the show. So thank you guys so much.
All right.
Yep.
Snakes!
Right.
Brothers of the Serpent, a household name in all four corners of the ancient world.
This is true.
So I just want to throw out a few news articles here. One, this is from Science Daily. Powerful electrical events quickly alter surface chemistry on Mars and other planetary bodies. So the summary, they're basically looking at like dust particles viewed mainly in terms of their physical effects, like erosion is what they normally look at them for, right?
Yeah.
But they're realizing that a quote, largely overlooked area of science is how these dust storms on places like Mars will create lightning storms and electrical effects, which will severely alter the chemical makeup of the atmosphere and of the surface and all this kind of stuff over time. And they just haven't really delved into this. So they're saying, like, from Venus to Jupiter to Mars, we actually have no idea how much this is actually taking place and how much it is affecting everything that's going on in the atmosphere and on the surface. So I thought that was pretty cool.
Are they saying there's lightning on Mars?
I'm basically what they're talking about is dust storms. So
Yeah, okay.
yeah.
So there might be
there's
lightning.
electrical effects.
Electrical
in the
effects,
dust
not
storms.
necessarily lightning, but electrical effects.
Yeah.
Okay, yeah.
It says, on Earth, dust particles are viewed mainly in terms of their physical effects like erosion, but in exotic locales from Mars to Venus to Jupiter's icy moon Europa, electrical effects can affect the chemical composition of a planetary body's surface and atmosphere in a relatively short time, according to new research from Washington University in St. Louis. So this is what they're looking into. I'm not going to read the whole article. If you're interested, go check it out at Science Daily. It's in Science News. But I just, was like, this just came out December 15th.
Yeah.
And I think we were talking about this on the podcast not too long ago. So
Yeah,
and it
and
may
about
have
how-
been during the Velikovsky.
Right, about how the lightning effects can crack down,
Yeah.
can change, the molecular structure of stuff and
Yep.
alter the atmosphere.
Yep. And this is another one. This, I probably should do this on Cosmographia, but this is from phys.org. A well-known Scriptard site. Cryosat reveals surprising ebb and flow of subglacial lakes. So they're looking at these subglacial lakes in Antarctica. I think the largest glacier in Antarctica. And they're realizing that these massive lakes actually completely drain out and then refill very quick. They're just like,
What?
Whoa, this is happening like really fast. Like in a number of, I think, let's see if I can get to this. What is
Man.
the timeline here?
Yeah. And where are they draining to? Out into the ocean, I guess? Just below the ice?
Yeah. Okay, so using more than 10 years worth of altimetry data from ESA's Cryosat satellite, scientists have discovered that the lakes beneath Thwaites, I don't know how to pronounce the glacier, the largest of which is over 40 kilometers long, drained in quick succession in 2013 and then again in 2017.
Oh, wow.
So, they drained and then refilled and then drained again in 4 years.
Man.
So I thought, hey, this is...
Yeah, that'll make some drumlins.
Yeah, exactly. Exactly.
Yeah.
Let's see what else we got.
Yeah, we should go over that on Cosmographia.
This one's really cool. The other story I had, I have another story about this sunspot. I guess I'll just pull that up real quick. This is from space.com. The largest solar telescope on Earth snaps the most detailed image of a sunspot we've ever seen. This was 4 days ago. And I just wanted to mention this because this image is amazing. And they go on to describe, what is happening here with the electromagnetic fields in this sunspot and how those are like pushing the plasma around and making these shapes that you see in the image. And the image is just absolutely amazing. So I just wanted to mention that. Go check it out. Really, really cool.
Yeah, the images.
Stuff coming from that solar
strange.
telescope. And then final story real quick this is from Scientific American. Get ready, folks. I can't wait for this technology. Eye treatment stretches mouse sight beyond visible spectrum.
Aha.
So we got to give this to Soraya for sure.
Yeah.
Tired of having to reach for your night vision goggles when you want to track someone's heat signature after dark? Well, biotech may someday come to the rescue for all of you aspiring spies. Because researchers have developed an injectable nanoscale antenna, which they've used to allow mice to see beyond their normal visual spectrum and into the infrared. The work appears in the journal Cell. Like all mammals, we humans are only able to see light in the visible spectrum, which includes all of the colors of the rainbow. That limitation is due to the photoreceptors in our eyes being only able to detect radiation with a wavelength of around 400 to 700 nanometers. And I would just point out that is less than 1 octave in that frequency range. Which means we can't see infrared and near-infrared light, which has wavelengths a little bit longer. And that got scientists thinking. So we are always curious on whether we can use any method or technique to allow us to be able to see near-infrared or infrared light. We actually developed nanoparticles, so-called up-conversion nanoparticles, that actually can effectively be activated by this near-infrared light. The scientists then tested their system in mice. The nanoparticles attach themselves to photoreceptors in the animal's retina. There, they absorb infrared radiation and convert it to visible green light. This enhanced supervision allows the animals to not only see in infrared, but to discriminate between different infrared patterns. So, for example, they could be taught to navigate towards horizontal stripes versus vertical ones, patterns that the researchers themselves could not see. When we do the experiments, sometimes it feels a little bit creepy because if you do not wear night vision goggles, and when we do the testing, we show the pattern to the animals. In fact, to our own eyes, we cannot tell any near-infrared patterns, but the injected animal could. They can use patterns to guide their behaviors very accurately and efficiently. They say the enhanced infrared detection did not appear to interfere with or supersede the animal's standard issue visual abilities. The treated mice were able to perceive these light patterns in the daylight conditions, clearly suggesting that nanoparticles working in parallel with conventional visible vision as well. The technology, in addition to its applications in military or law enforcement, might even provide a possible fix for color blindness, and best of all, it wouldn't need batteries. the nanoparticles remained active for as long as 2 months.
Huh.
So yeah, you're just like, you want to go on a hunting trip? Just go get this injection and you're good to go. I thought that was pretty sweet.
That is pretty sweet.
That's cool. That reminds me of this study that I read about, I think 3 or 4 years ago, something like that, where they were experimenting with humans, not mice, and they found that a very particular type of vitamin A would increase the human eye's sensitivity to low infrared.
Huh.
And it was they had to have a very restricted diet because they couldn't get any other type of vitamin A, or it would mess up the new vision that they were starting to acquire. So they were on this specific regimen of stuff they could eat, and also taking this like special vitamin A supplement. And they described it as, when you're looking at a sunset, instead of just seeing the reds and oranges and yellows, they would also start seeing greens and blues.
Wow.
In the sunset. Yeah.
Interesting.
So would you get these injections? Would you get them?
I mean, I'd probably try it. You know, just like I would just want to see what it would be like.
If it lasted longer than 2 months, because I don't need a needle in my eyeball every 2 months.
Yeah, but I mean, maybe just,
No, just to go check it
just
out.
one
right?
round.
Yeah, one round. Just go check it out. Just go
Hey,
look at the
get
world.
one every year right before hunting season. And you're good to go.
I mean, imagine, if you're a cave or a spelunker,
Oh yeah.
you don't need a flashlight.
Yeah, you
man.
see all the bats.
Yeah.
That's all you'd be able to see.
Well, if you can differentiate between the color,
Yeah.
between the heat spectrum wavelengths, then
Yeah.
you should be able to
See the walls.
Yeah. And the water, and be interesting.
And I'm assuming it would be more 3D than the conventional infrared goggles.
Yeah,
which
because
you
it wouldn't
just
be
can't tell distances.
projected onto a screen. That's actually going into your brain.
Right.
I would try it.
Yep, I would love to try it.
Yeah.
And I wouldn't want it to be like that forever. So I'm glad it's only like 2 or 3 months.
Yeah.
Right.
Because imagine you close your eyes and it's bright green
That's gonna be
because your
rough.
eyelids are warm.
It's going to be rough. Don't be walking around in the room while I'm trying to sleep. I can see you.
But I mean, just if it's seeing heat, when you close your eyes, your eyelids are warm.
Yeah.
So you won't have dark vision when you close your eyes. It'll be just green.
Well, and that depends on what part of the infrared spectrum you're looking at, right? So
Yeah.
like if they're just extending it to
The near infrared.
the near infrared, then you're not going to see heat from that.
That's true.
It's going to be like your security camera or something like that, where
Yeah.
it's just an additional wavelength of light above the red that we can see.
It wouldn't be thermal vision. It would just be
Right.
Yeah, the near infrared. Okay. But you gotta have the thermal vision.
But still, even if you could see in that near infrared, you would be able to see so much better at night, especially with the moon out
Yeah.
or anything like that.
Yep.
I mean, that's how those original infrared scopes worked. I think they used in like Vietnam. They were called starlight scopes.
Yes. Yeah, they just magnify the
use
amount of
the
light like 40,000
Ambient,
times.
yeah, the ambient light.
Yep. All right. Well, we ready for Tesla? We gonna do some Tesla talking?
Yeah, what you got?
All right. So one of the comments was when we were talking about, well, first I want to lay this out, like the idea of being able to have vehicles powered by the wireless power system.
Yeah.
And we had talked about
Problems with this,
the
yeah.
difficulties in having to constantly tune the antenna as it's moving through the field and staying in resonance. But, my initial thought was that airplanes, for example, would be too high up and cars would be too low to be at the layer where the electric field was. But say getting rid of that idea, just say there was places you could put it where airplanes could pick it up or they could fly through the field. Somebody pointed out, and I don't remember who it was in the Discord.
It was a YouTube comment.
Oh, a YouTube comment. They were pointing out, like, you have to have a ground, right? You have to have a ground, like, and yes, you do have to have a ground, but my thought was you can put a solar panel on a battery, and that's a closed system. That battery has its own negative and positive polarities.
Right.
So it is its own ground, right?
Right.
So
you have a reference.
Yeah, the negative pole of the battery is roughly the same potential as the rest of the environment. So you have your positive side, and that is where you're isolating the potential to go through your motors or whatever you're running, and then the return side or the ground is the negative pole of the battery, and you also connect that to the chassis of the vehicle or whatever it is. So it is a closed system.
Right. And if you think about it, a car is ungrounded because it's on rubber tires, right? It's not touching the ground.
But it has an electrical system.
It has an electrical system, and you can still receive radio waves for your radio, and the same with an airplane.
But isn't that a totally different kind of receiving than this system?
Well, so
it's a fluctuation in the electromagnetic field.
Yeah, and basically you have a capacitive coupling between that antenna and the ground as well, right?
Yes.
At least in terms of a car, right? So one, you have your reference, which is the negative on your battery, which is
all right,
connected to.
Let me ask the question this way. Could I run a wire from, like, say, the power system in my house, just one wire that, just the positive side to my car, and get power out of it without running a line back to the ground system? Because that's kind of what this system is supposed to do. It's conductivity through a conducting medium. So this is what we're talking about is the similar thing as me, like, trying to steal power from a power line without grounding the car. Can I do that?
Right. And so what Tesla, I think, was saying in his papers is that you can do that with a high enough potential.
Ah, okay. Okay. So the cars don't have to drag, like, grounding whips behind them or something.
Right. And the idea there was like you build up that potential to the point where it's creating its own electromagnetic field.
And from that field, you can induce current into any other conductor. That was the thing I was thinking of. If you had a plane that was not grounded, but it was able to be influenced by the field that was up in the atmosphere, you could use basically another coil. And since the plane's moving through the field, you would be able to induce electricity into that coil and put it into its own closed system.
Right.
But the question I had was, because there's a difference between the electric field and the electromagnetic field, can you, in the same way with an electric field,
induce a current?
Yeah. Because, like, the electric field is what is between two plates of a capacitor, right?
Right. And so in order to induce current, say, in a wire, if you just have a wire sitting in an electric field, it's not going to induce current in that wire until that wire is moving.
Okay, so it still will work by motion.
Yes.
Okay, so technically, if the plane was able to fly through the electric field, it could have a coil or something set up to where it would induce current into its own closed system.
Right.
Yeah, so my thought was, like, especially if you use a battery, like a battery system, because that is, you've already got your potential difference between the poles of the battery, and it's also extended, like you can charge the batteries, you can run the motors or whatever you need to, but if you leave the electric field, the batteries take over. But while you're in the electric field, they're being kept at full charge.
Right. And ideally you are getting enough power from that electric field to run everything and also charge the battery.
Exactly. Yeah. Yeah. So technically that is wrong. You don't necessarily need a ground.
Not to the physical ground.
Yes. Right. You need the difference in polarity. You need the difference in potential in your system.
But you can basically bring in outside energy without
Right.
without completing the circuit to the actual physical Earth.
Right.
That's
Yeah.
the idea. Okay.
Yeah, because one of the simplest ideas for me was like, okay, if I took a coil and I hooked it up to a light bulb, right? The two poles on a light bulb, the two terminals on a light bulb. I have this coil. It's a completely closed system. And if I dangle it from a string or whatever I do and I just wave it through an electromagnetic field, I can light up that light bulb. I don't have to connect it. It wouldn't matter if the system creating the electromagnetic field was grounded to the Earth.
Yeah. Yeah, I guess I was just thinking of it in terms of it's like these wires. It's conductivity. So, it's more like you're creating, we kind of talked about the idea that you can view the Earth as a small metal ball. Well, in this case, I was thinking that you would view this this charged layer of atmosphere as a hollow metal sphere around the planet.
Right.
In a sense.
So in that way,
it's a conductor, right?
right. And then you have a sphere around a metal ball. And at that point, what you have is a capacitor.
A giant capacitor.
Yeah.
Yeah.
Yeah. And so if you think about it, if you take that and flatten it out into just a flat plate capacitor, you have that electric field in between the two plates.
Right. And so anything you move through that, any conductor that you move
anywhere
through that
within
field.
that, between those two plates, and you're inducing a current.
Okay, so
That's
you
a
don't
good
necessarily have to be up in
The conductive layer. That's actually probably a bad
Right.
place to be.
Yeah. So other problems we talked about after the show is like the global problem.
The stealing power problem.
Yeah. So we were kind of trashing the idea that, that people say, well, this is a bad idea because you could easily steal it. And we were saying, well, like you got to tune them and everything. Well, yes, that's hard for like an individual to do. Maybe harder for an individual to do than throwing a hook up onto a power line and stealing power that way. But other countries could steal power.
Yeah. That was the big one right
That
there.
was
I
the big
realized,
problem.
Oh, you'd have to have an agreement across all nations of the world
Yeah.
that
If-
they were going to pay for this power.
Yeah, or contribute to it,
Or contribute to
whatever.
it, yeah.
Yeah.
It would have to be a global power system.
Because it would be no matter what. And so if all of our power plants were going into and this goes back to the question of would there ultimately be a free lunch after this system got up and running? In other words, would the sun be dumping so much energy in? I mean, it already is, but would that somehow tap into the conductor layer that we create up there, and just suddenly we don't have to be inputting so much power from our power plants? Then fine, let everybody steal it.
Yeah.
Right?
Let
So
people
if that's what people are worried about, that big business doesn't want to do this because ultimately it will be free power. Okay. But we don't know that for sure until it's tried.
Yeah.
But if it is the case that we have to run a power plant to continue keeping this layer of the atmosphere conductive, then another country that is not necessarily our friend could just,
Tap into
back
it.
engineer our system and tap into it and
Shut our power plants down. Blow all of our... I mean, you just put a huge load on the system and destroy all
they
of
could
our power.
put a huge load on the system.
Yeah.
Yeah.
So, yeah, there are problems. But like any kind of problem like this, I think they are not insurmountable.
Yeah, because I feel like we triggered some people by saying like it's not free.
Yeah, so this is another part of the discussion that we had, Kyle and I had, and with Archer after the show, is the definitions of free in this context.
Yeah.
So, and we've had discussions on this podcast before that words, it's important for everybody to identify the words and to identify the definitions of the words we're using so that everybody is on the same page when we're talking about what is and what isn't free power. I was making them. I was making the mistake of, in my mind, defining free energy as some kind of free lunch, as opposed to what I think most people think when they think of like Tesla, wireless power, and free energy as I don't have to pay for it. Those are two different things.
Right.
In physics, free energy is like an impossible thing, you know? And I had some discussions with people on the Discord about this, and people were saying, well, like a solar panel is free energy. And it's like, well, no, it's not, because you have to build it and it costs money. But yes, it's one of those things that, technically speaking, once you've paid for it up front and you install it, it's free in the sense that there's no more, you don't pay any more money until 25 years later when you got to replace it or whatever.
Right.
So,
or a hailstorm comes and destroys all your panels.
Yes, that's right.
So
Nature destroys it in some other way.
Yeah, what you're getting at is the difference between free energy in a physics sense.
Yes. And that's how I was defining it when we were talking.
Versus free energy in a monetary sense.
Right.
And
or costs. Yeah.
Costs.
Yeah.
The way I look at it is there is no such thing as
either one of those.
Because even if you build solar panels, that costs a lot of money. And
Yeah.
then you still have to maintain the system. And it's not just the solar panels. Because like in that sense, free energy, like the sun is giving us free energy all the time. It's heat, it's light, it's, the river next to your house is free energy, dude.
Yeah.
Go get it.
And that's
not free.
Basically from the sun. Yeah.
Yeah, that's right.
Yeah.
The sun is making the river flow.
Right.
Right. It's all. So yeah, the energy is all around us. It is not free to convert it into a useful portable energy.
Right.
Mm-hmm.
But
and then in the physics terms, even the sun is not a free energy device.
That's right.
Because it's doing all kinds of entropic things to do that, to make that energy, which in terms of physics makes it not free.
But on the other hand, you've made the argument, we've made the argument multiple times that the free lunch idea is like, you've made the argument about perpetual motion. You're like, I'm not talking about forever.
Yeah, yeah.
But if I can turn this thing on and it runs for 10 years and I can get energy off of it, that's great.
That's great. Yeah.
That's a free lunch. Right.
Yeah. So in the very specific definition of perpetual motion in physics, it's an impossibility. But if I can build a machine, like you said, that'll run for a long time that I can suck energy out of, then I don't care if it isn't technically perpetual motion. Just like the sun is a free lunch in the sense that you don't have to do a whole bunch of, you don't have to build that energy from the ground up because it's all around you, and you just need to figure out, you got to build things to figure out how to harness it.
Yeah.
Mm-hmm. Just like, the food that we eat, plants or animals or whatever, are technically a free lunch because you don't have to build them atom by atom. You can just go and get the food. It's the plant makes the leaf, and then you can have a salad.
Right.
Right. All you got to do is go out there and harvest it and then cut it up. And guess what? That turns out to be a lot of work. Yeah. But it's still, in a sense, free in the sense that it's most of the work has been done by natural processes. But it isn't. But in terms of physics, none of this is free in the sense that there aren't costs associated with generating the energy being generated, just like the sun. It is burning stuff. It is going to run out of fuel. It is going to make phase changes, and eventually it's going to stop doing that, which tells you it's not a free energy device in terms of physics. But it is a free lunch if you can figure out how to harness it.
Yeah. So I think the main point about the free energy idea, I would say in the terms that I think most people imagine it, which is like they're not paying a lot of money for their energy.
Yeah.
Like the energy, in other words, is we build this massive Tesla type system and then the sun starts powering it and we don't have to use our power plants anymore.
Yeah.
We still have this massive infrastructure to run, to keep the towers working, to keep all of the materials. It's like once you build a bridge, it's free bridge. No, that bridge needs maintenance all the time.
Free bridge.
It's got to be repaved. It's got to be checked by engineers to make sure it's still good. So the infrastructure involved in any power grid is going to be expensive, and nobody's going to go and do all that work for free.
Right.
So it's and wind, you buy a bunch of wind generators and solar generators, they're extremely expensive. And you set that whole system up to run your house and everything. And yeah, you pay all the money up front. And now you're not paying a bill every month. But you will have to maintain that equipment.
Yep.
Batteries are required. Those are very expensive and have to be replaced. And so,
and there's an enormous infrastructure of factories and mines and transportation that maintains all of the stuff that's required to have those generators and those batteries. So yes, it's not free.
So
there
I think
are costs.
I think a better way to talk about it is more economical, right? It needs to be what's the other word?
More efficient.
More efficient.
Yeah.
Yes.
Yeah.
So more efficient.
Would it be more cost effective?
Power generation and power transmission is great, and we should work towards that. It'll never be free.
Right. And also, I think we're coming into the segment here, but the final thing was people were saying that Tesla was working on free energy devices, and I guess the point I want to make is we weren't saying he wasn't. We don't know everything he was working on. I don't know if anyone does. And then, of course, there are plenty of conspiracies about people stealing his work after he died. And, we didn't go into any of that. We were specifically looking at the wireless transmission of power that he was working on and his laboratories that he built to sort of experiment towards that aim.
Right.
We did not go into the larger story of all of that other stuff. It is there. It's harder to confirm some of that stuff. It's interesting in some cases. And whether or not he was working on free energy or not, I don't dispute. I mean, but I think that during the course of the podcast, Kyle brought up a great point, which was that a lot of what Tesla was doing was so greatly increasing the efficiency of existing systems that it did seem like free energy in some cases at the time. It's still not
right.
It's still not actually free, but was Tesla working on some kind of free energy or what people, I don't think he was ever working on 0 point.
But he did talk about the idea, which is one way they spoke about the ether, which was a prevailing theory of the time.
Yep.
Which I kind of think modern science has gone back to with quantum field theory. They just don't call it the ether. But his point was that, hey, this like unlimited energy is all around us in every, mathematical point in space, basically. Like,
yeah,
he didn't say that in those words, but he's saying just like in every place, in every possible imaginable tiny speck, there is an infinite amount of energy, right? He said things like that.
Yeah.
And this was based on the theory of the ether and all that, what does light travel in, all this kind of stuff, which, there are obviously other theories about it. But his idea was like, if we could tap into that, then all of our energy problems would be solved. But again, you come down to what it takes to build. Once you get that energy, how do you transmit it? How do you,
do you have to convert it? What's involved in getting it where it needs to go? All that stuff.
And all of these things will require lots of materials and people working on ideas and
Yep. Probably blowing some things up, setting things on fire.
But yeah, I mean,
all the stuff that usually happens when
technically it's true. I mean, atomic energy is there and it's in every atom.
Yeah.
There's a lot of it. It's very hard to get it and it's incredibly expensive.
Yeah.
And dangerous.
Yeah. With techniques we have today. That's right.
Yeah.
All right. Anything else on that subject?
Yeah. But we can take a break.
All right.
We'll be right back.
And welcome back, ladies and gentlemen. Brothers of the Serpent podcast. Second hour already. Time goes fast. Yeah.
So fast.
Fastest 2 hours in podcasting. So we're continuing on the Tesla discussion here for a bit. I think Kyle was going to talk about telegeodynamics.
Yeah, so the other power transmission idea that I know about from Tesla was telegeodynamics, and that was one of the last things that he talked about before he died in terms of, power transmission. And I think generally he was always looking for ways to, utilize the natural medium to get this so-called what we're calling a free lunch and transmit it everywhere on the planet. And so telegeodynamics was something that he went back to after basically had lost all of his funding. He didn't have, I don't know if he had a lab at the time, but it was kind of near the end when he wasn't, it was after Colorado, it was after Wardenclyffe, all that stuff. And before he did those things, those big ideas that he had been working on, he was messing with the mechanical oscillators, which were basically just like a reciprocating motor that was steam powered. And those are in his patents as well. I don't know the patent numbers, but it was a single piston inside a cylinder, and the piston was just moving back and forth. And so he would control the frequency of the piston's oscillations and create this incredibly energetic vibration, mechanical vibration. And so he was experimenting on, and this, people call this the earthquake machine. And I think it's been on Mythbusters, because he had made a comment about how he could take down the Empire State Building with 5 pounds of air. And the air was because he was using a steam power at the time. And he had actually made an improvement on the steam engine because there was timing issues with the steam engine. And if things got out of timing with the steam engine, you could have explosions and stuff. And so he built this sort of self-timed steam engine, which ended up becoming his mechanical oscillator, which he started doing these other experiments on. Where was I going? So he had made this claim that he could take down the Empire State Building with 5 pounds of air, which the air would be the fuel to create the oscillations in the piston. And I think Mythbusters did a thing on it where they put a mechanical oscillator on a bridge, and they ran it, and they were trying to tune it to the bridge, to the bridge's fundamental frequency or whatever. Yeah. And then at the end, they were like, yeah, we got the bridge vibrating a little bit, but you could never take this bridge down with this little thing. Well, in my opinion, that's a problem of amplitude, right? I mean, yes, you would need to have sufficient amplitude. You can it's just like the wine glass. You imagine the woman, singing at the wine glass and it breaking. Well, it has to be loud enough and it has to be the right note. Those two things. In other words, it has to be the right frequency and it has to be of sufficient volume, if it's a sound vibration, to get the glass ringing, which is basically distorting the glass enough to cause it to fracture. So could you take down the Empire State Building with 5 pounds of air? I don't know, because we don't have one of Tesla's mechanical oscillators, but there are some pretty convincing patents that show how he stepped this machine up and up again and up again. And basically you could do it many, many times. And so you have a small piston with with 5 pounds of air, and those oscillations, the exhaust go into a larger piston that's harmonically tuned with the smaller one. And eventually the larger piston starts going, and those oscillations then go into a larger one, and you're dealing with harmonics here. And so the bigger it gets, the more inertia it has. I still think you could do this, but the telegeodynamic system was him kind of taking that idea to the grand level in the same way that he did the electrical power transmission, which was to build a mechanical oscillator of sufficient size and have it anchored to the planet at the right place on the right material. And you get this thing going and you're inputting these vibrations into the Earth, and you're minutely tuning these vibrations to be harmonically tuned to the Earth's mechanical resonances. So this wouldn't be like a fundamental, like the lowest frequency resonance of the Earth. It would be a much higher harmonic, which is less destructive. Like the fundamental frequency is the most destructive, whereas the higher you go up in harmonics, the less destructive it is to that structure. But that basically this would create a mechanical oscillation throughout the planet that could then be picked up by a similar machine that was built in another location. And if that machine was built in another location, was tuned to that frequency, it would eventually start going on its own, picking up those vibrations that you've input into the planet from another location. And then you would be able to take that energy off. And suppose, and the main idea is that you've got like this starter motor, which is what gets the oscillator going. And that's what starts getting the high harmonic induced into the planetary vibrations, the already existing vast amount of energy in the planet's mechanical vibration. And so you're just getting this vibration going, but it's sustained by the Earth's resonance. And then in that sense, you could then stop running the starter motor and start taking power off of these oscillators. And it will all be mechanical energy. And the other things that he talked about was that using this technology, you could also send messages, because you could modulate that resonant frequency similarly, like the way we do it with radio. You could modulate it with amplitude, you could modulate it with frequency, and make complex wave patterns that you could then take the carrier wave out, and you'd have left over that modulated resonance, which could be, like radio. It could be spoken, people talking into a microphone. It could be messages, whatever, any kind of information you wanted to send, and it would go everywhere on the planet. Even boats at sea could pick it up from the water.
Yeah. EarthNet.
Yeah. And the other thing he said about it was that you would be able to use this same technology to look down inside the Earth to see where any kind of ore, like, we need to find some more iron. You just go around with this, what he called it was a sort of divining rod. Yeah. Which you could put on the planet to discern what types of materials were down there and how deep they were.
Yeah, since the frequency
is everywhere, and
you know exactly what it is.
Yes.
Yeah.
You would know exactly what that frequency is. So however it was modulated by the materials in the planet, you'd be able to see that.
Yeah. You could use that to map the deep structures.
And I think that, technically speaking, that is all true, but is it feasible to do, and is it dangerous? I'm sure it would be dangerous, right? Like there'd probably be unknown effects and things that would happen.
Yeah.
But, who knows?
Yeah, it seems like it would probably do some interesting things to the faults, right?
Yeah, it could.
But at the same time, once all the stresses of the faults were relieved after starting the system going, then they would constantly then we would not have earthquake problems.
You might have a more stable system because the energy from what would be the earthquakes is being absorbed into that.
Yeah, or constantly, or the oscillation is constantly relieving the stress. Yeah.
Yeah. So yet to be discovered. We should try it on Mars. But I've always been fascinated by that one. I loved that one. And the point of describing all of that was that, yes, he was, like, it seems to me, just from my research, is that Tesla was always looking for ways to get the free lunch, right? It's not a free system in terms of money It's not a free system in terms of physics, but it is free for long enough that once it gets going, we don't have to keep inputting and doing a lot of work to input the power or to, I don't know.
Yeah.
The other point.
Yeah, I mean, once you get the swinging, all you got to do is touch it to keep it going, right?
Yes.
Yeah.
Which takes a lot less energy.
Right. And so I guess going back to the once again the other example I thought of previously in the free lunch idea was that it's essentially a hydroelectric dam is free lunch, right?
Yeah.
The river is flowing, you don't have to pay for that.
Yeah.
So we already do, in a philosophical sense, we're already getting free energy.
Especially when they have the dam, the dams. There's like 5 or 6 of them, and you have dam 1, 2, 3, 4,
Right,
and
you
5,
just keep
keep tapping off the same river flowing downhill in multiple stages,
Yep.
And you let it run through the pipes. It spins the turbines on dam 1, and then it comes out the bottom of that dam, flows down the river for a while, and then goes into dam 2 and does the same thing.
And we don't have to do any work to get that river going. I mean, that's all being done for us. So it's kind of like it's hard to imagine from that perspective that there's going to be a way that we can convert energy into the type that we can use, and that system's going to be free in terms of money. Because those systems are everywhere, but they're not free in terms of money. The systems where the energy is just readily available. You just have to build the stuff to change it to what you need, right?
Yeah.
That's exactly what we do.
I need to turn this flowing river into a spinning thing.
Right.
And that requires some costs.
Now we can always come up with better ideas on how to get that stuff and to how to transmit it. But anyway, I'm becoming a broken record at this point.
All right, so one question the watcher posted earlier was, would this Tesla system change the atmosphere? And I mean, this is a hard question to answer. I don't know if any of us have the answer, but would this change the atmosphere drastically, and would we disrupt possibly badly the atmosphere by doing this and then drawing on it? What do you think of that, GMA?
I mean, there's always unforeseen damages when it comes to energy, like with windmills disrupting and killing tons of birds.
Yeah.
Or, same with solar energy, blinding birds, or like the big solar water boiler plants. Have you seen, I think they have one in Australia where it's a giant array of mirrors that points up at a giant water tower, and they heat the water up to steam to turn turbines.
Uh-huh.
And you can fry anything that flies into the path of that focused light beam.
Right. So
I mean, there's hazards and risks in any kind of energy generation, and I think in the case of where you have like an electrified atmosphere, what could there be some kind of lightning type discharges that occur because of this?
Yeah.
Especially say more frequently. I mean, we already see more frequent lightning strikes on tall buildings, hence the need for lightning arresters. So, would that increase the probability of stuff like that happening, where you have lightning striking certain areas with high frequency?
Yeah. And then would there be weird interactions with normal storms in this layer?
Right. Because I mean, you're talking gigawatts of power, Marty.
That's right. 1.21 gigawatts.
And I mean, going back to the whole Mars thing, with sand blowing across the surface is a static generator.
Yeah.
So I think it's very feasible that there's lightning on Mars, given the giant dust storms that are there, because you have basically an insulator rubbing against a non-insulator and stripping electrons, right? So like the say there's sand on Mars. I know we think there's a great quantity of iron oxide in the crust or in the surface because of its red color. So there you have an insulator and a non-insulator that are constantly rubbing together in a storm. That's I can totally see that being a giant static generator.
Yeah.
And if you have what we already have as a giant static insulator in our own atmosphere, or a static generator, sorry, in our own atmosphere, what's an additional layer of charged, like supercharged air going to do to that?
Yeah. Yeah, so it's in the realm of speculation, but
Yeah, absolutely.
it's almost certainly positive to change things and to alter things and have strange effects and unforeseen consequences.
Yeah, and that's one of the downsides, in my opinion, that this type of system is almost untestable except on a global scale.
Yeah.
Same with the telegeodynamics idea. It's like, okay, so we could do this, we could build something to really test this, but it would have to be on a global scale to really test it. And then if there were bad unforeseen consequences, I mean,
They could be really bad.
They could be really bad. They could be global in scope.
yeah. So,
Yeah.
but I mean, in the name of science, I kind of want to give it a shot.
We should try it.
But that reminds me of what you're talking about with the dust. One of my favorite things about static electricity is the triboelectric series. I've talked about this before, I think, on the podcast, but that is you take any group of materials and you can put them in series based on their tendency to shed or absorb electrons, right?
Right.
Take on electrons or give off electrons. And that would be a triboelectric series. So the two materials that are furthest apart in the series are the two materials you'd want to put together if you wanted to create the best static charge, because one of them's going to want to shed tons of electrons and the other one's going to want to take them on or something like that.
Right.
So yeah, it's when I look at stuff like that and you realize, like, okay, if you took all the materials that we have on Earth and you put them all together in this giant triboelectric series, it's like that's one category of interesting electrical phenomena, right? That certain materials want to shed them more so than other ones.
Yeah.
And so you have this difference between them, and they're not really in harmony with each other. And then you end up with this overly charged thing and one that doesn't have enough or something like that. And that kind of stuff, when I see those types of things, I'm like, okay, there's got to be a free lunch here somewhere. Right?
Yeah.
You take that category of stuff, and then you take the category of when you look at different materials and how they have different thresholds of becoming a gas or a liquid or a solid at different temperatures and different pressures. And you can put all these materials, you can line all these materials up and look at their thresholds and see, okay, that one's at this temperature, this one's at this temperature and pressure. And then you've got this thing over here that, they want to exchange electrons at this rate. And, you go through the different categories of these things, and it seems like there would be a way to sort of build some kind of chain out of all these different categories of the way energy wants to exchange or be exchanged between materials. And you should be able to build something that would ultimately result in, like, the free lunch idea, right?
Yeah.
You're getting the
It went
most...
around and around and around, and you could siphon energy off of it without depleting the system. Yeah.
Yeah, for a while.
Yeah.
Right?
Right. Yeah, until you stripped all the electrons off of one of your materials, and then you'd have to just swap that plate out and keep going.
And especially if you had one that was then you had something about the natural environment that was helping replenish one of those things or multiple of those things, the day-night cycle.
Yeah.
And we see this type of stuff all over the Earth all the time. And it's always, you could trace it all back to the sun.
Yeah.
But there are these massive exchanges and not exchanges, they're transductions of energy that are happening on a daily basis, basically because of the day-night cycle. We see this huge transduction of energy with water, right? Getting hot and cold every day and night, creating the clouds, which creates the rain, which runs down the river because of gravity. And those, there's just, this stuff is happening in the natural environment, and there's so much energy transductions taking place all around us all the time that, it seems like we should be able to get a lot of energy off of this process.
It's all around us all the time. And how do we get it?
Yeah. So no one's denying that.
Yeah.
There is so much energy around us all the time, and it's always changing hands. How we tap into it, I mean, people have been trying to figure that out for a long time. But I'm sure there's plenty of ideas out there that have not been tried yet that could be very effective.
Yeah, or have been tried and have been squashed.
Yeah.
Who knows?
Yeah.
All right. Well, I have this article that was sent to us. It was from the... Is this the... Well, this was sent in an email. Let me make sure I've got the person who sent this. I think this was from... Yeah, this was from Daniel, who sent this. So thanks, Daniel. Appreciate it. This is a great article. This is from getpocket.com. I haven't heard of this website, but this is a cool article. So it's called If We Weren't the First Industrial Civilization on Earth, Would We Ever Know? Fossils and objects are unlikely to survive more than a few million years. Searching for chemical traces of industrialization offers an intriguing alternative. So the Silurians, I'm not sure if I'm even saying that right. It's from Doctor Who. The Silurians are a species of lizard-like creature that appeared in the cult science fiction TV show Doctor Who. They achieved industrial expertise about 450 million years ago, long before humans evolved on Earth. The Silurians are fictional, of course, but the idea of advanced prehistoric life is an intriguing one and raises a variety of interesting questions. Not least of these is this. If an industrial civilization had existed in the past, what traces would it have left? So we get an answer thanks to Gavin Schmidt at the NASA Goddard Institute for Space Studies in New York City and Adam Frank at the University of Rochester. These guys have a name for the idea that an industrial civilization may have predated humanity, the Silurian hypothesis. They study the signature that our own civilization is likely to leave behind and ask whether it will be detectable millions of years from now. Their conclusion is that our probable impact on the planet will be palpable, but in some ways hard to distinguish from various other events in the geological record. Their work has some interesting implications for how we should study Earth and the impact we have on it. The research should also help astrobiologists decide what to look for elsewhere in the universe. Schmidt and Frank began by setting out just how little we know about ancient Earth. The oldest part of the Earth's surface is the Negev Desert in southern Israel, which is 1.8 million years old. Older surfaces exist only in exposed areas or as a result of mining and drilling operations. Given these constraints, the evidence of activity by Homo sapiens stretches back some 2.5 million years, not really that far in geological terms. The ocean floor is relatively young too because ocean crust is constantly recycled. As a result, all ocean sediment postdates the Jurassic period and is therefore less than 170 million years old. In any case, say Schmidt and Frank, the fraction of life that gets fossilized is tiny. Dinosaurs roamed Earth for some 180 million years, and yet only a few thousand near-complete specimens exist. Modern humans have existed for just a few tens of thousands of years. Species as short-lived as Homo sapiens, so far, might not be represented in the existing fossil record at all, say Schmidt and Frank. What of human artifacts, roads, buildings, baked bean tins, and silicon chips? These too are unlikely to survive long, or to be found even if they do. The current area of urbanization is less than 1% of the Earth's surface, point out the researchers. We conclude that for potential civilizations older than about 4 million years, the chances of finding direct evidence of their existence via objects or fossilized examples of their population is small, they say. But there is another type of evidence. Our civilization also leaves a chemical footprint. Schmidt and Frank are interested in industrial societies, which they define as those capable of extracting energy from the environment. By this definition, humanity has been industrial for about 300 years. Since the mid-18th century, humans have released over 0.5 trillion tons of fossil carbon via the burning of coal, oil, and natural gas, say Schmidt and Frank. This has had a significant impact on the planet. Since all this carbon was originally biological, it contains less carbon-13 than the much larger pool of inorganic carbon. Releasing it is therefore changing the ratio of C13 and C12, a signature that could be or should be visible in the geological record. The temperature increase caused by this carbon is about 1 degree centigrade. This too should have an observable signature, the way it changes the isotopic ration of oxygen-18 in carbonates. Agriculture and nitrogen cycling in fertilizers is also changing the isotopic signature of nitrogen. And agriculture and deforestation both increase soil erosion, as does increased rainfall due to global warming. So ocean sediment should be changing too, thanks to eroded soil washing into the sea. And on top of all of this, use of metals such as lead, chromium, rhenium, platinum, and gold has increased thanks to mining activities. And these will presumably be flushed into the ocean at greater rates than before industrialization. Humans are also changing the fossil record. There has been a widespread increase in small animals such as mice and rats. This ought to be noticeable, as will the increased extinction rates of other species. Large mammal extinctions that occurred at the end of the last ice age will also be associated with the onset of the Anthropocene, says Schmidt and Frank.
Wrong.
Right, yeah, some of this is whatever. Then there are the chemicals we make. Humanity has released large volumes of synthetic chlorinated compounds into the environment, along with huge volumes of plastics. Just how long these chemicals or their daughter products will be detectable isn't clear. There is even the possibility of a nuclear signature, perhaps from a civilization-ending war. Curiously, the effects of such a war may not last long in geological terms. The half-lives of most of these elements are just too short to be relevant on this timescale. Two possible exceptions are plutonium-244 with a half-life of 80.8 million years and curium-247 with a half-life of 15 million years. These would be detectable for a large fraction of the relevant time period if they were deposited in sufficient quantities, say, as a result of a nuclear weapon exchange, say the researchers. Schmidt and Frank conclude that humanity's existence should be visible in the geological record. The anthropic layer in ocean sediment will be abrupt and multivariate, consisting of seemingly concurrent specific peaks and multiple geochemical proxies, biomarkers, elemental composition, and mineralogy, they say. However, this signature may not be unique. The researchers have identified a number of events in the geological record that look similar to the impact humans are having. For example, a sudden global change occurred in carbon and oxygen isotope levels some 56 million years ago in an event known as the Paleocene-Eocene thermal maximum. This coincided with a large increase in carbon levels and a temperature rise of between 5 and 7 degrees centigrade over a period of 200,000 years or so, which is a mere sneeze in geological terms.
Okay, but the rise in temperature would create a rise in carbon levels because it would be outgassing from the oceans.
That's right. Yep.
Sound scared there a bit, but
no, I don't think they mentioned carbon yet.
He said that it was a
global change occurred in carbon and oxygen isotope levels.
Oh, okay.
Yeah, and this coincided with a large increase in carbon levels. You're right.
Yeah,
and
in carbon levels and temperature.
And in temperature rise. Nobody knows what caused this event, but one idea is that at this time, igneous rock in the North Atlantic expanded into organic sediment, heating it and releasing carbon. This North Atlantic igneous province later became Iceland and related landmasses. That's not the only unexplained change in the geological signature. Numerous other changes in temperature, carbon deposits, ocean salinity, and so forth are awaiting explanation. There are undoubted similarities between previous abrupt events in the geological record and the likely anthropic signature in the geological record to come. Of course, none of these events indicate the presence of an earlier industrial civilization. The Silurian hypothesis cannot be regarded as likely merely because no other valid idea presents itself, say Schmidt and Frank, who are keen to head off unconstrained speculation. Nevertheless, their work raises some intriguing questions and points to the value of further research on how long synthetic compounds will survive in the environment. We recommend further synthesis and study on the persistence of uniquely industrial byproducts in ocean sediment environments, they say. Are there other classes of compounds that will leave unique traces in the sediment geochemistry on multi-million year timescales? That's interesting work written up in an entertaining paper. It explores an unusual idea that has the potential to change the way we think about humanity and places our impact in a broader perspective. It also provides a background for astrobiologists studying other planets. Mars apparently was much wetter once and warmer. If it ever hosted an industrial society, this paper maps out some of the signatures that might show up in the geological record there. And Venus, too, was once more hospitable. Then there are the oceans of Europa and, ultimately, planets around other stars. Nevertheless, our industrial civilization may be unique in the universe, but much more exciting is the possibility that it is just one of many, perhaps millions of others. And Schmidt and Frank had set out some of the groundwork for finding them.
That's really cool.
Yeah, so that, well, we're out of time. I have to go to the final segment because I got a continuation of this topic that I want to go into for a bit.
All right, folks.
We'll be right back.
Back, ladies and gentlemen, sadly for the final segment of the final hour, fastest 2 hours in podcasting. Your friendly serpents here at Brothers of the Serpent Podcast. And yeah, so you went over that story.
Yeah, so we're kind of all over the place
yeah,
here.
we're all over. It's a tangent cube of science.
Yeah. I have multiple topics I wanted to talk about. I was going to sort of use that story to segue into one of them that was going to then segue into another. So do we have time?
Maybe we need to do 2 of these episodes.
Maybe. I mean, but it probably won't take me long. I just want to. I've been going through some physics recently. Right. Okay, so two main things I want to talk about that they don't really require a ton of discussion. I just really find this fascinating. Number one, because of this article where at the end they're implying like this will help astrobiologists in what to look for in exoplanets.
Right.
Okay. So I was looking into the exoplanet situation. It's weird how this kind of came and went in the news, in the mainstream news pretty quickly. Like the first exoplanet discoveries were sort of announced like, oh my God, they found this Earth-like planet. And now no one's talking about it anymore. It's like it's become, boring. But looking at the cutting edge research of the people who are still doing this, and now there's a lot of them. I mean, exoplanet research has become a big deal in astrophysics.
Yeah, they just found one that was emitting radio waves.
Yeah.
I saw that.
Did you know that Alpha Proxima has a planet? The closest star to us has at least one, and they say that it's not only Earth-size like, but it's also in that star's habitable zone.
Oh, wow.
How? Okay, so in terms of the size of the universe and the
I don't think it's true because it's improbable.
Right. What that implies is that these are everywhere.
Yeah.
The fact that we have one going around the star that's closest to us, and that is a binary system. So it must be an interesting sky. But I'm just saying that's fascinating. 4 light years away. I mean, that's an incredible distance. You'd have to if we're going sub-light speeds, you'd have to build a generational ship or some kind of cryo sleep system to get there. But this could be possible.
Yeah.
And I mean, sending a robot there is also a possibility. If you could get it up to,
let's start now.
If you could get it up to some fraction of C, and people are already talking about this, sending a tiny camera. They're like, okay, if we send something small, all it is a camera with a big battery and an antenna so that it can fly past it and take pictures and send them back to us.
Yeah,
right? And then, but they think we could, with the right systems, and I think they're talking about using lasers, like very powerful, either orbit or Earth-based lasers that you just shoot the laser at this thing for all of the years it's traveling to keep accelerating it. And it could reach some fraction of c, so that by the time it reaches that, now there's no way of slowing it down, so it's going to be going by real fast. But it could get there fairly quickly if it's going at some fraction of light speed, and then it could take some pictures and send them back to us, and then keep going.
So selfish. I mean, we should just write a message, put it on a probe, and send it out there.
A slow probe, a regular slow probe. Yeah.
Because okay.
That'll take millions of years, probably.
Yeah, but whatever. It'll finally get there, and then if there's an intelligent, species with civilization there, they'll find it and they'll know that we were here.
Yeah, that's true.
That's at least we're telling them like, hey, dude, we used to be here. Not sure if we're still there anymore.
This might have shown up a little late, but
or we might pass it on our way there in the future and be like, hey, that was the probe they sent 1,000 years ago.
Yeah,
which would be cool too.
The other interesting thing in the search for exoplanets, and I love how they're doing this. What you have to do is you have to have a really, really sensitive scope, because there's like multiple problems in terms of looking for these kinds of planets. They're going to be around a star, and it's like, I guess you can think of it as like if I took a quarter and I put it on the ground in front of a car with its bright headlights on facing you, and then you were standing, hundreds of feet away looking towards that car with the headlights, would you be able to see that quarter?
Only in the right position where it was reflecting off the quarter's face.
Or if this quarter could magically float, it passed in front of the headlights.
Yeah.
Right? And then even then, if you're far enough away, you wouldn't see the shadow of the quarter.
Yeah,
you would have to detect it with very sensitive things that could say, well, the light dimmed a little bit here.
You'd have to have a pretty advanced monocle.
That's right. Yes, advanced monocle systems. So that's how they're looking for exoplanets. They have made surveys now of, over 100,000 at least stars nearby, where they look at them. And they basically just look at a bunch of them all at once. So the people talking about this are like, this is not a normal telescope that zooms in. These look at large pieces of the sky, because you just got to look at everything.
Yeah.
And then they use computer assisted searching through the data, because it doesn't take a picture. It's giving you a ton of data. Then the computer, they build a algorithm or a program that goes through the data and looks for, does this starlight dim? Then that tells them that we should focus on that star, right? So they've done this with over 100,000 stars. And the first thing they had to do was eliminate a bunch of stars that are too variable,
right?
Because it messes up their detection system, right? And the detection system being the computer program. The computer program goes, yeah, that star is brightening and dimming, but that's actually because the star itself is a variable star. So they had to eliminate a bunch of stars like that first. But those stars might still have planets. Mm-hmm. But I'm not sure that a star that's that variable would be able to support life like us, maybe something else, right? So you wipe all those stars away, whether they have planets or not. They don't even look there because they can't tell, because the instruments aren't sensitive enough. Then they look at the remaining stars and find out which ones dim and which ones don't. Then they focus on the dimming ones, and this is where it comes in, where they start trying to find out what kind of planet is this. And then you have to wait for the planet to cross in front of the sun again. And that, of course, depends on how far away the planet is, how big it is, all that kind of stuff.
And so the ones that they're finding more often than not are ones that have very short orbital periods.
Right. Yeah. Yeah. There's one that's basically a gas giant that orbits its star in less than an Earth day.
Yeah.
It's so
All
close.
in gas.
Yeah. But then they do analysis on the light from the star in order to try to figure out what the planet is composed of or what's in its atmosphere. This is where it gets interesting, because just like that story said that I was reading, they're now looking for signs of gases in the atmosphere that can't be there by any known natural processes other than life.
Yeah.
Like oxygen, for example, is one of these.
Like the gas that they found in Venus's atmosphere or whatever.
Yeah, the swamp gas.
Yeah. Swamp gas from Venus.
Swamp gas on Venus. Yeah. But oxygen is one of these. Oxygen likes to bond with everything,
Yeah.
right? So you have to have something constantly replenishing the atmosphere or the oxygen in an atmosphere for there to be a lot of it in the atmosphere rather than bonded to all the other stuff. So oxygen is a signature of life, a possible, and there could be natural processes
That keep oxygen replenished.
Yeah.
Yeah.
Same with carbon, all that stuff, right? But so what they're doing is they're just looking for signatures where they could say, okay, not only is that planet Earth-like, it's also in the Goldilocks or habitable zone. In other words, it's in a place where they think that water can be in a liquid state for a large amount of time on places on the planet. But also, does it have gases that might indicate life itself on the planet itself? And all of that comes by not ever being able to actually see the planet. They never see a shadow of the planet pass in front of the star because the scales are too different. They're just looking at how the spectra of the star changes when the planet crosses in front of it.
Yeah. It's crazy.
The other thing that's really interesting about this whole search is that they found so many stars that seem to have exoplanets around them, and it's more than 1% of the number of stars searched, given that you erase all the stars that are variable. Okay, so even those might have planets. So given that you survey 100,000 stars, and then a certain number of those are too variable, so you get rid of those. The remaining stars, let's say that I don't know what the number is. Let's say it's 80,000. You had to remove 20,000 because they're too variable. 1% of those, you're seeing what looks like planet crossings. Now, the first thing I think of is that the planet crossing has to be from our perspective.
Yeah, if the plane of the ecliptic is tilted and
there are plenty of orientations of systems out there where the planet will never cross the star from our perspective. So if 1% of those stars have planets crossing, then that almost implies that all of them have planets. Mm-hmm. Because there are a hell of a lot more orientations these stars can have than the one where the planet will cross in front of the star between us and its star.
Right.
So
good point.
That's really interesting. And when I was listening to an exoplanet researcher talk about this, she said that the number of stars with exoplanets that they've found in their survey, and given that particular thing, that they have to be in the ecliptic of that star, and that system has to be right so that the planet crosses it. The number they found implies that somewhere between 50 and 100% of all stars have planets.
That's freaking awesome.
So that's a lot of planets. And then also the fact that the closest star to us happens to have at least one exoplanet. And not only that, but that exoplanet is Earth-like. And I think when you look at their definition of Earth-like, they're talking about in terms of mass and that it's not a gas giant. It's probably a rocky world.
Rocky world, yeah.
Right. But, they'll say that a planet with 3 times Earth's mass is Earth-like. Mm-hmm. And if the gravity on the surface of the planet is 3G, that's not Earth-like enough for me to want to live there. That's too, you'd be too heavy.
But how hollow is it? Because the gravity could be the
totally,
same.
yeah, good point. It could be expanding and it could be hollow.
It could have a lot of mass, but just be hollow. So it's big. Gravity's not that much.
That's right. Balloon exoplanets.
That's right.
So anyway, I just thought all that stuff is fascinating, and none of this is really in the news, but the exoplanet research that's going on right now is really interesting.
Well, I'm seeing a lot of exoplanet stories, honestly, in my feed, and now I feel bad because I'm like, it's probably boring. Because every time I click on them, it's like I wasn't thinking about it in the broader sense that you're delivering this idea, right?
Yeah.
I was thinking of it on an individual basis, and when I click on those stories and start reading about them, I'm like, okay, they know very little about this planet, but there's another one, right?
Yeah.
And they're all excited about, the scientists working on it are like, yeah, this one's sort of like, it goes around the sun like pretty fast, or it's star or whatever. And
yeah.
They tell you a little bit about the star, and then they tell you what little they know about the planet.
Yeah.
And then it's 200 light years away, and I'm like, okay.
Yeah, it's too far. We don't know anything.
So it's on an individual basis. It is boring, but as a research project as a whole, it's actually not boring at all, and I will from now on be clicking on those stories so that I can get a more broader picture of the
Yeah.
understanding of what's going on. So thank you.
Yeah,
for that.
and I also think that what they're finding out about the arrangement of other planetary systems around other stars is completely changing, it is massively upset the long-standing standard model idea of the formation of these systems. They don't the old idea of they're slowly accreting whatever from a disk around this. It's not really isn't really working out with what they're finding now. That hasn't been. But there aren't, as far as I can tell, there aren't anybody trying to figure out what is going on. But for example, the gas giant that goes around its sun in less than a day, that doesn't work in the
And anything but Velikovsky's
gas giants being that close to the sun. People are like, that's wrong. Your data's wrong. But they went over it, and multiple people figured, looked at it from different observatories, and they're like, yes, this is what seems to be happening here. So there are interesting systems out there that are just really strange, and I think it's going to revolutionize the way that they think star systems and planetary systems around those star systems form.
Cool. Which probably would put our system into one of those extremely low probabilities situations.
Right, yeah.
To make it impossible.
And one question I tried to find answers to, but I just couldn't find anything on it. I maybe I need to keep looking. Was there anybody out there thinking about what our system would look like to an intelligent advanced civilization on one of these other exoplanets we're looking at? Like when they look, what I want to know is if there was an intelligent advanced civilization that was exactly the same as ours, whatever they look like, maybe they're made of octopuses, but their technology was exactly the same level as ours, and they're 40 light years away on some exoplanet, and they're looking at our sun. What would our system look like to them? Would they only see Jupiter and maybe hints of Saturn, or would they be able to tell that there are like all of these worlds here? That's what I wanted to know. In other words, I was trying to find out, like, okay, so you find hints of planets around these other stars, and sometimes you say there might be 2 or 3, but could there be a lot more than that? And you just can't tell. Like, I mean, I was thinking about how Pluto is tilted, and it's really small. And maybe is it possible that you can be in the right place where you could see all the other planets in our solar system transiting our sun, but you'd never see Pluto cross it because it's kind of tilted in the wrong way.
Yeah. Yeah, I can see that. I mean, maybe after a long period of time, if this whole solar system is doing this wobble, then maybe at some point you'd be able to see it.
Right.
But I don't know.
Yeah. And would they only basically, in other words, with our technology level, would we only be able to see Jupiter and Saturn?
Yeah.
And maybe.
Well,
Neptune.
I mean, they're saying they're seeing these rocky planets that are much smaller than Jupiter.
Yeah.
So I don't know.
Yeah.
But that's really cool.
Yeah, I couldn't find anybody talking about that, but they were saying things like doing these projects has made them start thinking about what are they seeing when they look at us, but they didn't say like this is what we would be able to see if we were them, which is what I was looking for.
Yeah, where I was going to go with that is, all right, let's build a giant something that we can do something really big out there that might give them a little
make a big giant foam finger, and put it in front of the sun and wave
giant foam finger space waver.
Well, they do have this project that they're working on called Starshade, which is really cool. And the idea is, and this is like one of those, so they came up with it in the 70s, and like, it kind of reminded me of that scene in was it Armageddon, where they're looking for ideas for how to, get rid of this asteroid that's going to hit or whatever, and these guys come in and they're like, you unfold these giant mylar sails, and they're trying to unfold this foil in the room, and he's like, all right, get out of here, let's talk to somebody who's had less coffee.
Yeah,
it reminded me of this idea because that's basically what they're talking about. You fire off a package that has something similar to that, along with a telescope that kind of flies behind it, and at some point way out there, this package sort of explodes or detonates or whatever, it unfolds into this giant flower-shaped thing. And then you align it very perfectly with this telescope where it basically is blocking the light of the star that you want to look at so that you can actually see the planets. You know, and you have to put it, I mean, it
has to be where the ratios have to be right.
Yeah, it has to be way out in front of the telescope. And it has to be perfectly aligned with lasers and all that stuff. And then, you know, and it can't be wobbling, and there's all kinds of weird technical problems, but they're working on it. They're actually working on this.
Oh, that's awesome.
They're like, yeah, we're the star shade. You know, you need to hold your thumb up and block out the sun so you can see the other planets around that star.
That's cool.
Yeah. Which is how you see Nibiru. We know this. You hold up your thumb.
You got to hold your thumb up
and you block out the sun and you can
see the second sun.
See the other. That's right.
And the Anunnaki are coming in the wall. Yep. That's great. So that was going to lead you into another thing, or is that where you were going?
Yeah, I had one other thing I wanted to talk about. Because we've had these conversations before about redshift and measuring distances in the universe. And this leads to interesting ideas about dark energy, right? I mean, the reason we have the idea of dark energy is because, and okay, everything I'm about to say is all standard models. So everybody, all you Electric Universe people, just be quiet.
You shill.
I don't know how, yeah. It's still fascinating and interesting to know the way it works. But when you're looking out at the universe, you can, because of the way, you know, because light speed itself is a constant, you know, this is, everybody knows this, but the farther something away is, the light that we're seeing is older, right? So the question is how do you tell how far away things are? That therefore tells you how old it is, right? You got to build a map of the universe, you have to be able to know the distances between things. And triangulating is kind of something you can't do with something that far away. So we've talked about redshift, and we've talked about the redshift problems in Halt and ARP, sorry. And but there is another way that astronomers and astrophysicists measure distance. We've talked about main sequence stars and how they use the light for that. But there's another thing called a type 1a supernova. Okay. So I was kind of diving into this topic because I wanted to know why this, in the same way that a main sequence star, we question like, well, how do you know what this thing is, right? Well, the idea of a type 1a supernova is really interesting. And basically you start with a white dwarf, which is a small star like our sun is probably going to become a white dwarf. Okay. So at some point, a small star with comparable mass to our sun, so like one solar mass, it burns for billions of years, and eventually it kind of swells up into this big red giant thing as it's running out of fuel. Now, the way it's running out of fuel is in the fusion sense. It's moved most of its hydrogen into helium. It's fused it all into helium. Maybe there's some carbon, but it doesn't have the temperature or the mass and the temperature, therefore, and the pressure required to begin the next fusion process to move it up the chain, which is, I can't remember, silicon or something. It doesn't make it to iron, is what the point is.
Okay.
It reaches a point where it has no more fusing fuel because it doesn't have the required temperatures and mass and energy levels, therefore. Okay. So then it kind of collapses. And in the collapse, it does a nova type thing. It blows off a whole bunch of material, and you end up with about one solar mass or less compressed down into the size of an Earth-like object, Earth size. So you think of our entire sun squished down to the size of Earth. Now it's not burning anymore, okay, but it's still really hot. All of that, the residual fusion energy, the resulting explosion from the compression, and then just the pressure of it collapsing down into this thing. And it's going to be mostly made of carbon and helium, okay, in this state of matter that they call degenerate matter. And it's degenerate in the sense that, and I don't really fully understand this, but basically a lot of the electrons are forced down into these quantum states, and every quantum state around all these atoms becomes filled. And the energy level, the quantum energy level is the maximum quantum energy level of each one of those states is maxed out, so they don't really have anywhere else to go, and they're kind of stuck. But they're incredibly hot, and they're moving very fast. So you end up with this material called electron degenerate gas. Okay, this is a white dwarf. Okay, they reach that electron degenerate gas state only if they're within a certain mass limit, less than 1.4 solar masses. Okay, this is called the Chandrasekhar limit. I think that's his name. This is an Indian guy who figured this out. He was on his way from India. He was like 20 years old. He was on his way from India to England to be educated. And on his way there, he figured this out.
Ding! Oh my God.
Yeah.
Figured it out.
Yeah. Basically, that limit states that at 1.4, roughly 1.4 solar masses and less, a star will collapse into a white dwarf and retain this electron degenerate matter gas state. And it will basically, from then on, just cool down and cool and cool, and eventually become what is called a black dwarf. It becomes totally cold. It's just this material that's, you can't even describe it. It's not metal or crystalline. They call it a gas because all these electrons are in these weird quantum states, but it's incredibly dense, right? Something like, I think I was reading 10,000 metric tons per cubic centimeter.
Wow.
Right? So whatever you would call that material.
Heavy metal.
Yeah. But what's interesting is that a lot of these stars end up in binaries around other stars. And they're really small, but they have this incredibly high surface gravity. It's not as high as a neutron star. A neutron star has more solar mass. It will collapse, and then it has enough gravity to pass the electron degenerate matter state and into the neutron degenerate matter state, because it actually has so much pressure that it shoves the electrons into the protons, and they cancel each other out and become neutrons, and then they still call this a gas, right?
Wow.
But that's a neutron star. It has more mass, and then if it's got even more mass, there's some limit, it becomes a black hole because the surface gravity gets so high. But with a white dwarf, if it's orbiting another star, or eventually begins to orbit another star, it can leach material off of that other star.
Yeah.
So now you have this tiny ball of incredibly dense material that's still cooling down from whenever it stopped being a sun. It's no longer on fire. It's just incredibly hot. It's glowing. It's hot. It's white. But it has to have less than the Chandrasekhar limit of mass to maintain this state. So if it starts orbiting another orbiting another star that's still in its big gaseous state, and normal stars maintain
slowly accumulating mass,
right on top of it,
star.
which is adding pressure and heat until eventually it passes this limit.
Yeah,
and then something catastrophic takes place in the star, and fusion begins again. But because of the way, and I completely can't understand this or explain it, but because of the way this quantum electron state of this material works, it can't expand.
Can't go back.
There's nothing thermal. Like a normal star has thermal regulation of temperature because it can swell and shrink and swell and shrink based on what's happening in this. The material of a white dwarf can't do that according to standard model physics. Obviously, nobody's ever watched this happen up close, right? All of this is based on particle theory. But if it gets up to this limit, the star starts fusing again, and then it explodes in a supernova as a result. What they call it unbinding the star completely. In other words, the energy level of the fusion, because everything's so crushed,
it immediately reaches the thresholds. And
yes,
just,
it's this gigantically massive immediate chain reaction, and since everything is so mashed close together, it all happens all over the place at once, and boom, the thing blows up in what's called a Type 1a supernova. And they are, because of the way this process takes place, how they're always this same size below this limit, and they don't explode until they reach this limit. Every supernova of this type is almost exactly the same as every other supernova of this type. This is called a standard candle in astronomy. So I found that fascinating. Okay, because we've argued about this, like, how can you just decide what this looks like when you don't know, right? Well, we still don't actually know, But the theory, you can look at it and it's showing you, okay, this is the processes that take place. And because of the processes that take place, the explosion always happens at the exact same mass
Yeah.
with the exact same degenerate material, you know. Now, it's not exactly the same because there are little differences. Most, they say these stars have to start out not being able to fuse carbon into the next thing. So they're going to be mostly made
Right.
of carbon and helium.
Yeah, the ratios may be a little bit different, but
Right.
for the most part.
Because newer stars made out of stuff from older stars that did make heavier material will have that heavier material already in them at form. They won't be just pure hydrogen at
Yeah.
the beginning, right? So once they've done with all their fusion stuff, they still have like little bits of
Yeah.
heavier materials in them. So there is tiny variation, but it's theoretically a tiny amount. So the idea of a standard candle is that you can look out into space and it's easy to identify type 1a supernovas. Their light spectra is always the same. The magnitude of the brightness is always the same. And so you can use this aside from redshift to measure distances to stuff. And this is actually how the theory of the accelerating universe and thus dark energy came about, is looking at standard candles all over. They did a huge survey of standard candles all over the universe, and they actually some people did a lot of work in trying to narrow down the, what would you call it? The error ratio, the error on the magnitudes of standard candles, right? I don't understand it, so I can't explain it, but
aren't they using the redshift of that standard candle light to tell the distance and therefore how old it was?
They're measuring it by magnitude.
Oh, okay, to tell how far away it was.
Yeah.
Okay.
Instead of redshift. This is what I'm saying.
Okay, I got you. That's what I was wondering. I was like, how do they? Okay, so
Yeah.
it's magnitude. Yeah, because
Yeah.
they know that they were like the theory is they would all be the same magnitude. So when they see some that are much lower magnitude, they're like,
If they're
okay,
really
that's
far away. Yeah.
Okay, that's cool.
Yeah.
Maybe there was a lot of dust in there.
I know. There's problems, but I keep reminding myself of what you've been telling me. You're like, dude, this is, it isn't perfect, but this is what we have, right? So you look out there, you're like, and I think that I've been reading these people's work and listening to them, and they all acknowledge the problems.
Yeah, for
Right?
sure.
Yes, there's all kinds of issues, and they tried their best to what can we do instrument-wise, experiment-wise, theoretically-wise to narrow the
variability.
The variability, because first they did a bunch of work on showing look, that you can't call them a standard candle when there's this big range in magnitude that can take place, theoretically speaking, if this has a whole bunch of uranium in it from some other supernova, right? Whatever. So they worked on that, and then they measured distances to things using these standard candles all over the...
Did they compare it to the redshift data?
That I don't know.
Because it'd be interesting
Yeah.
to see. It's kind of like what's building in my mind is sort of like you've got dendrochronology and then you've got carbon dating.
Yeah. You want to match them up.
And then you want to try to match them up and say, okay,
Yeah,
so
let's correct
we got to
for this and
calibrate.
correct-
Like this
yeah.
one's a lot more accurate, but there's not as many of them. Whereas redshift, you can look at anywhere in the sky and calculate distance by redshift. So you've got one that's like you can use in a lot more places, and then you have the other one that's more isolated to specific areas, but you can cross-reference, and then you can get a calibrated date.
Yeah.
That's cool.
Yeah, and I don't know.
I know. I mean, I'm obviously a cosmopolitist.
Well, this is so the like I said, they were looking at large pieces of the universe and looking. Okay, so you have to go back. You've got 30 years of data of all these different observatories looking at, and some of them are looking. Well, they're wide scopes, like the exoplanet ones, where they're just looking at giant sections of the sky instead of focusing.
Yeah.
Right. So now you've got standard candles happening because a type 1a supernova isn't a common occurrence in a galaxy.
Yeah.
But it's a common occurrence in the universe.
Yeah.
Okay. And they're sort of supposedly, theoretically speaking, easy to identify. And once they happen, then you can start using them to measure stuff. You
Right.
say, okay, here's the acceptable, here's the error that we know we have. This one's plus or minus 14. This one's plus or minus 8 because of what we're seeing in the spectra and all this kind of stuff. And then you start looking, and then you start building a 3-dimensional map of the universe. And then you have to take into account the distances also equal the time, right? So if one they're measuring and they're like, all right, that looks like it was 5 billion light years away. Well, it also happened 5 billion years ago.
Yeah. Yeah.
So given that the observable / visible universe is roughly like 13 or 14 billion years across, light years across, they look as far back as they can for standard candles, all the way out as far as they can. And maybe they were using redshift because this is how they found the acceleration.
Yeah. Yeah. Yeah.
Okay. And what they found was that, let's see, should I go from the beginning? Yeah, let's go from the beginning. So farthest out, and they're measuring standard candles getting closer and closer to us. And they're seeing a travel velocity, a redshift, and a moving away from us velocity based on the redshift and the standard candles and the magnitude and the distance. And then they get to about 5 billion light years out. And then the ones that they're measuring closer to us have accelerated, and they continue to accelerate as they get closer. In other words, the acceleration of the universe caused by dark energy started about 5 billion years ago.
Like halfway
It
back.
wasn't happening before that. This is
That's
where
weird.
And it was so astonishing to them that this is where dark energy came about. That the explanation is not an explanation. They're just like, this is a placeholder that basically no other force in the standard model of physics can explain this large scale universe wide acceleration of stuff that started about 5 billion years ago or halfway through the age of the universe. And that's even weirder to me than that this was anomalous acceleration from the beginning.
Right. Yeah. Yeah.
It's like the
absolutely.
universe, the Big Bang takes place. Now, so you're looking at the cosmic microwave background. There's a dark period when there were no stars. Then stars start showing up. Those stars start making galaxies. You eventually start seeing standard candles. You start seeing type 1a supernovas all over the universe as these stars, some of these stars become white dwarfs and then eventually explode. And the expansion of the universe at that point is a normal, what you would expect expansion resulting from a gigantic explosion of something. But when you get to 5 billion years ago, everything starts speeding up. Do you think so? Given all that, does it seem to you more likely that that dark energy is a thing, or that there's something wrong with the measuring process?
Well, no, I'm just taking it based on the data. Like, so the first thing that comes to my mind is that your entire description of the star in the beginning is analogous to the whole situation. So it's like, because I like the idea of symmetry, right, across all the entire
you
thing.
like supersymmetry.
I like symmetry. So it's like there are thresholds, right? So whatever this thing is that is the entire universe also has these thresholds that are reached, and then something new is
Something
now
new
taking
happens.
place,
Yeah.
right?
It's
So it's
definitely
just like
something new.
you've got your star, and then it reaches some threshold, and then it collapses. And so there's this, if you were on the nucleus of an atom, and you're looking out into the rest of the materials in the star, trying to figure out what was going on, and you go way, way, way back, and you see that everything was acting one way while it was a big star going through fusion, and then something changed, and suddenly now you've got all these
Crunch, yeah.
So it kind of looks like that, and I think that's cool. Like that, there are these like some threshold was reached in the entire process of
That
whatever
caused a new process to emerge.
Yeah, that this new process begins, and we're seeing
That's
that take
exactly
place.
what they're saying, and they're calling it dark energy.
Yeah, that's
and,
cool.
And what's interesting about it is they have these ways of like, okay, well, let's look out at the universe. So we see all this material, all the material we can see. And then there's the cosmic microwave background. There's an assumed amount of other types of energy that we can't directly see, but we can assume is there, like, light having been shed from stuff. Then there's the dark matter that seems to be holding things together that we can't find, but it seems to be there because we see its effects. And then there's the dark energy. And the dark matter plus the dark energy make up the vast amount of material / energy in the universe.
Right.
Almost all of it.
Right.
That normal matter, that what we think of as like between 2 and 5% of the actual amount of stuff in the universe,
Right.
if these two processes indicate a matter and an energy.
Right. Or is there an overall effect that is ultimately the result of what we normally see as matter and energy that is at work here? We're just not seeing the manifestation of it in the way that we recognize.
Right. We only can see it in enormous structures. So the last thought I have on this topic, and then I'm done here, is given all that, they've decided, you know, with all these measurements, and now we're like, okay, so the universe began to accelerate again, expanding, not just expand faster, but the acceleration of the expansion is accelerating. It's like getting faster and faster all the time. This is only really visible in the really large distances between the things. This is where it's theoretically taking place, is in the really distant, like actually empty space that's between galactic clusters and stuff like that. But what's fascinating to me, and this was just like some little tidbit that I came across, is that, you know, we got this age of the universe at 13 to 14 billion years, which is also the distance of light, the size. You know, that's how far away the cosmic microwave background radiation is. But given all the acceleration that's taken place since then, the new calculation for the actual non-observable but actual size of the universe is more like 47 billion. I don't know the exact number. A much larger number, because like the CMB, the source of the cosmic microwave background, has been accelerating away from us this whole time, and then it started getting faster, accelerating away from us 5 billion years ago. So it's actually way farther away now than it was.
Than it
right?
appears.
But what's really fascinating is that based on all of these calculations, the estimated actual size of the universe at this point, given all the acceleration, versus the observable universe, which is what we can see, the difference between those is just about pi 3.14.
Wow.
It's not exactly pi, but it's so freaking close that I'm pretty sure it's actually pi. And
it's the way pi represents itself in nature, which is never exactly perfect.
Right. They were saying it's like closer to 3.2, right, than 3.14. But that just makes me think that it's probably actually much closer to pi than that. We're just not.
Yeah, we're
not quite measuring it correctly. Yeah. That is also like now. Okay, now you're like, what? What is going on?
And at the end, you have pi.
That's right. All right.
Can I get a bonus section?
Oh, yeah.
All right.
Yeah, we'll have a bonus section.
All right.
That took longer than I thought.
That's all right.
Standard candles, people. Interesting stuff.
Yeah.
To me.
Giant snakes!
Special fifth bonus section. My physics rant went on too long, so Kyle still has stuff to say.
The bonus section.
Can I get a bonus section? Yeah, take it away.
Okay, well, first, Watcher made a point earlier during the break, and I want you to come on and make this point. Make it better than you did during the break there.
Yeah, I'll see what I can do. By the way, hi, everybody. I'm here.
All right.
So the thing that I had thought was that when discussing tapping into the resonance of the Earth and its frequency, and then using that to build stepwise towards some sort of massive usable energy source, if there was a highly advanced ancient civilization that had done that, when the Earth's year changed from 360 to 365 days a year, that resonant frequency also changed, and in an instant, your entire technological infrastructure comes to a screeching halt.
Yes. And we're like, looking at the pyramids and that kind of stuff. Is like, okay, was this some kind of giant power generator or some type,
and experienced some catastrophic failure.
And it's all shut down.
Yeah.
Because whatever they were tapping into is no longer the resonant energy in the system. So that's what I wanted to talk about, but in a different way. A friend of mine sent me this video. He sent me a link to on Twitter, and I guess I can send that to the Snake Bros and you can retweet it. But it's a simple setup with a group of metronomes, the old type of metronome that actually has the swinging lever with the weight on it. All the metronomes were set to the same tempo, but they were all started at different times. So they're all out of sync with each other, but they're actually sitting on a plate that is on rollers. So the whole body of the thing can also shift back and forth with the motion of the metronomes. And you watch this video, it's like a minute long. They all start at different times, and by the end of the minute, they've all synchronized to each other. And I think that type of situation, or the demonstration, is illustrative of the way these large systems work. And I think you were pointing this out when we were talking with Laird about, we were talking about the inferior conjunction and showing the same face and all this kind of stuff. And you were asking Laird about, if a planet came in, would every other planet have to shift and be in different positions? And I think that this video is a very good analogy for the answer to that, which is yes.
Okay.
They will do this over time. Now, how long will these processes take? I don't know. You know what I mean? We're looking at this like just with the metronomes. It takes about a minute or whatever, and maybe it could take longer. One of them is still, so when you're watching the video, 4 of them get into a pretty good synchronization, but one of them's still way off. And as that one is being brought in closer and closer to the frequency, it starts to kind of shift the other ones out away from each other again.
Yeah.
So you're seeing the effects of all of the different bodies on all of the other different bodies, and that can be erratic for a while.
So I'm trying to put this together because the way that they became synchronized was because the entire plate could shift back and forth.
Yes.
Due to their motion. So once you had 2 or 3 of them going the same way, it would overpower what the other ones were doing, and then the whole thing would start to wobble just a tiny bit, and that would start to bring the other ones in sync, and then eventually you've got 4 out of 5 in sync, and it's going back and forth pretty good.
Yeah, but
that one eventually brings the 5th one into sync, but it has to move all the other ones too.
Yeah, but say the 5th one is in sync, but almost opposite to the other ones,
so it's
right?
canceling out.
It's canceling out a little bit, but not enough because the big plate is moving in the wrong directions, and so it's slowly trying to negate that one metronome's motion until eventually and then when it gets out of the opposite synchronization, it starts to throw some of the other ones off for a little while, and then they all finally sync up. So it's like, when I see that type of thing, I'm just like, yes, this
is how the
universe works. Okay. So if there was some planet or some rogue body that rolled through the solar system, it would throw everything out of whack. But eventually the overpowering, or the connection between all of them to each other through gravity is going to synchronize everything over time, right? That's the way I imagine it. So I love that video, and I'll send it to you so you can tweet it out on the...
Yeah. And I can put a link to it in the show notes.
Yeah, and also, what is it? The one that I saw is just called spontaneous synchronization.
Yeah.
So yeah, it's like going back to Brett's point about the power system, right? Once you have this overall synchronization between all these bodies, like, yes, why couldn't you tap into that energy and use that as your sort of, free lunch type of thing? And then, of course, if something came along and changed the frequency, Like this wouldn't work if one of the metronomes was a different frequency. It
Yeah.
would always be out of sync.
Right. If the weight had been up or down.
Right.
Yeah.
Yeah. So I don't know. I love that. I love that idea and the the symmetry, the idea of the symmetry. It's not that I look at the universe and say it's all going to have this perfect symmetry, because obviously it doesn't. There are asynchronous aspects, but when you look at the overall big picture, I think you're going to see, generally speaking, symmetry throughout.
Yeah.
Right?
Yes. That it if it's asymmetrical, it tends towards symmetry.
That's right.
Using larger systems.
Larger and larger systems,
Okay.
right?
Okay.
So
I can. Yeah.
So going back to your point, or your explanation of this acceleration at whatever it was, 4 billion years back or whatever, you take this idea into consideration that okay, this is there are all these independent functioning systems like galaxies, and then there's bigger ones, galaxy clusters, but then there's the whole entire universe. So some threshold was reached somewhere in the universe, and that sort of brings, it spreads throughout the whole thing. Just like in the collapse of the star, it doesn't all exactly collapse at the same time. It's going to start somewhere, and it's going to spread, and it may be really fast to us.
Yeah.
But you change your scale and you go way down, and these,
Into Planck time or whatever.
Yeah,
it's going to take a long time.
Yeah. So you see this in the universe, and to us looking back, it's like it all happened roughly like 4 billion years ago or whatever. Well, there's a lot of time for that to actually take place.
Billion years, yeah.
It's a lot of time for that to take place throughout the entire universe. So it could have started somewhere and spread.
Yeah. And also, since the measurements are being taken from a type of event that is a short, doesn't last very long and is sporadic. So you're basically taking spot measurements. Mm-hmm. So you're not getting a nice, smooth gradient. You have to extrapolate some kind of curve from the points you're getting, and the points are the supernovas, right? And so you're like, okay, there's one over here, and then there's one way over here, and now, we got a whole bunch of them, and now we got to try to figure out how far away they are, and then that builds a graph in a three-dimensional space, and then you see the acceleration and you extrapolate a curve. But you're right, the appearance of a sudden acceleration may not be quite like that. It may have been some kind of resonant system getting going or adjusting to some other resonant process.
Yeah.
But these kinds of phase changes do kind of have like cutoff points, right?
Yeah.
So it does, you might say, well, between 4 and 5 billion years ago, and you're like, well, a billion years is a long time.
Yeah.
But for the entire universe to start accelerating within a billion years, that's pretty drastic.
Yeah. Yeah, but I mean, it's like nucleation of crystals.
Yeah.
Right.
Yeah.
You can have a liquid that is in a state where it's at the threshold, it's ready to become a crystal, but there's no nucleation.
Right.
There's no nucleation
tap
site.
it. Yeah.
Yeah, and then once that first bond happens, or transition phase change
Yeah, then it-
happens,
then it
and
happens very
in
quickly.
between two atoms, boom,
Yeah.
it just
Yep.
spreads throughout the rest of the medium
Yeah.
as a somewhat of a chain reaction.
Yeah.
So, just like there was another sort of analogy it was like when you were describing the situations that these scientists are dealing with when they look out at the universe and they're trying to look at these little planets and they're having to look at the star and the dimming of the star and all this kind of stuff. So
Yeah.
it's all this indirect observation.
Yeah.
It reminds me of the exact same type of problems we deal with when we're looking at the quantum stuff.
Yeah.
Like, you can't actually look
at it.
at that thing. You have to kind of look at what it does to this thing.
Yeah. You're looking at the effects it causes on other things.
Exactly.
Yeah.
And so it's there again, there's this interesting sort of symmetry, and that's kind of, that's a broader idea. It's just about us and how we have to deal with things. But
Yeah, because we're in the middle of the scale.
Yeah, I just noticed that type of thing all the time in physics, and so yeah, it's like to me it's that's why I like, I'm always bringing up cymatics, right? I'm the cymatics guy.
Yeah.
Because something about the way that works, and no matter how detailed you get about what's going on there, it's always seems analogous to me to these larger effects that we see, and even effects that we see in the quantum scale. I like to find those types of things. So when I saw that video of the synchronization, I'm like, okay, yes, this is a principle.
Right. Yep. Well, I think it can be explained that basically something like a blender got turned on 5 billion years ago.
Touche.
It was full of mercury.
And space started flying apart.
I'm sure there's spinning mercury in there somewhere too. Watch her.
Oh yeah, GMA, what's your thing? Was it walls?
Yeah. He had walls around his projects.
Yeah, that's right.
Oh yeah, one wall still feasible. 2 walls, you're getting there. 3 walls, it's probably not happening.
Highly improbable that project will ever be completed.
So anything else? Because I realize I've got a few more things that I could say that I forgot.
Well, I was just thinking, what if you could set up along one of those boards on the rollers with different weights for the pendulums representing the different planet sizes.
Ooh.
Yeah, I do think.
And start them. You could start them at the yearly periodicity for each of the planets, so they all start at their own frequency, and then you could do things like roll a weight across the board to see what that does to the interacting oscillations.
Oh, that is cool.
Yeah.
All right, fine.
I've got to try
I'm gonna have to buy 8 metronomes. I could get 9.
We could probably do it with pendulums or something. We could make in metronomes.
Well, the metronomes, they remain constant. That's the point.
Yeah. Okay. Yeah. The spring-loaded thing.
Yeah.
No.
Well, and that's probably like you said, Russ, pendulums might be better because you can start those at a frequency, but then they'll change their frequency over time based on the other pendulums that are swinging versus all the metronomes trying to stay at one.
Yeah, that's true.
Yeah.
And then you could use the different weight ratios.
Yeah.
It's a question of weight ratios. There we go again. You can't say that without throwing in the Monty Python joke.
It's not a matter of where he grips it.
Anything else, GMA? I feel like I did all the talking during the Tesla thing. I kind of just screwed you over, bro.
No. That's really all I had about the pendulums.
All right, cool. What else you got?
Going back to standard candles in this Type 1a supernova, recently, and this is very recent, so people are still shouting at each other over this, but there have been a couple of Type 1a supernovas detected, and I don't know how they figured this out, but based on the data that came in with the various scopes that they're looking at the supernovas, they determined that these didn't take place until they were much over the limit. Like one of them, they were saying might be even 2.2 solar masses before it turned into the supernova, which is way above the Chandrasekhar limit of 1.4. And that may be a huge problem in terms of being able to use the magnitude of these things to measure stuff, because if it has that much more mass, then that changes a lot of stuff. And if there's that much variability. So now they've seen 2 or 3 of these that they think had a lot more mass than so now there's all these different ideas, like maybe this particular one that had 2 point whatever was spinning incredibly fast.
Yeah.
And there's other possibilities that maybe it was a actually two white dwarfs colliding. So they only very briefly.
Yeah.
So that the addition of mass took place all at once, and it was a whole other white dwarf, and so it was like two white dwarfs, and then boom, explodes.
Right.
But now they've seen 2 or 3 of these, and now they're kind of wondering, like, have we completely miscalculated the whole concept of standard candle?
Ooh.
So that's interesting. And I had one more other thing that I can't remember now. So just have to wait on that one.
Yeah. Well, there you go. Bonus section complete.
Yeah.
Thoroughly enjoyed it. I love doing these episodes of just random tangents.
Oh, I was about to sit back like we were done. No, I got to finish this. All right. Thank you guys for sticking around for the bonus section. As you know, you can get a hold of us, brothersoftheserpent@gmail.com. Check out the website, brothersoftheserpent.com, for everything related to the podcast. Give us reviews at Apple Podcasts. That really helps to spread the show around.
But wait, we just got like an affiliate type of deal.
Yeah, so it hasn't completely finished yet. But
okay.
yeah, so TeePublic contacted me about our TeePublic store and offered us a deal on getting an affiliate into the affiliate program, which apparently will give us more of the profits from each sale. So that's going to be great. Hasn't completely happened yet, but supposedly once it all goes through, I'll get a special link. I can put that on the website, put it in the show notes, whatever. And
So if you're going to buy something, wait.
wait until we've joined the affiliate program. But thanks to all of you who have bought snakeskins. Yeah, she did mention it. She was like, "You call them snakeskins?" I was like, "Yeah, come on."
This doesn't affect the hats, though.
That's right. So join the Discord. That's where all the snaky conversation is happening these days. And we have this new project I wanted to tell everybody about. This is a new thing Kyle and I have been talking about. Episode 200 is coming up. So this is 178. So episode 200, if everything goes right and we continue to publish one episode a week-ish, it should happen in about 6 months. And I was thinking it'd be cool to do like for the episode 200, it would be cool to kind of do a retrospective sode, like let's and get a whole bunch of clips together from older episodes that are favorites, of montages of us saying stupid things and me mispronouncing words, all the Monty Python jokes we've ever made. Obviously, this would be a huge project for Kyle and I to do it ourselves. So what we want to do is crowdsource it. So all of you listeners out there, if you have favorite sections of the shows, of any show, all the way back to, in any of the back catalog episodes, if you can get the number of the episode and the timestamps, from this time to that time, and then you can either join the Discord, and there's a special channel to post that stuff in, which will help us later when Kyle and I go to put the show together. We'll be able to search and find all of these clips and go get them and put together a show out of them. Or if you don't want to join the Discord, you're not interested in that, you can always email us with, episode 200, put episode 200 in the title of the email, and then put your, this is the episode number, here's the timestamps for as many as you want. And little descriptions of what they are would help too. So we want all the listeners, or as many people as possible, to be involved in this project. So when we come together for the episode 200 show, it's going to be it'll be awesome and hilarious and a lot of fun, I think. So we have 6 months to do it, so no hurry. But if you're one of those people who's still going through the back catalog, keep this in mind, because we need people back there looking at those older episodes, getting the good clips out of there. So
yeah, that's going to be fun. Good idea.
If you do join the Discord, there's the episode 200 channel now where all this is happening. And people are already posting timestamps and clips and coming up with ideas on how to build montages of us doing stuff. So that's... join the Discord, which is run by Jeff. Check out the Library of the Serpent. Thanks to History Shift for making all of our videos. Thanks to Pod Doodles. Check out Cosmographia, which is the podcast we do with Randall Carlson. And we thank you guys so much for sticking with us.
Really appreciate it.
Yep.
It means more than you can possibly know.
That's right.
This is favorite day of the week.
Which is why we love you.
Always have.
Always will.
Good night, Adamu.
Get back to work!